Hello everyone, welcome to the post-contest discussion for Starters 166. I'm Jay and this is TLE Eliminators. Let's start with the first question. So the first question was Chefland Library. Basically in this question we had a story that there's a library and in the library there's a penalty system for late book returns. And for each book, if you return a book on ith day and if you return the book by say 2 days late, then you would get a penalty of 2. And if multiple books were returned on the same day, then the highest penalty among the books is counted. And basically chef borrowed n books and you're given an array of integers I, and that array said that starting from 1 to n, the ith index said that this book was written I days late and it was written on the day A of I. And now we have to calculate the total penalty that chef has to pay. And this was the input format and these were the constraints, like T was up to 1100, that is around 1000. N was up to 10 power 5, A of I was up to 10 power 5, and sum of n over all test cases was less than equal to 10 power 5. And let's start with the sample test cases. So we'll be solving the first problem here. Okay. So if you now look at the first test case, which says you are given this array. In the first test case, you are given this array. The A basically is 1, 2, and 3. And if you look at I, this is someone has. Okay. Now, and the I is over here, like the first element I would be 1, second element I would be 2, third element I would be 3. What does this indicate? Well, the first element indicates that the first book was written on day 1 and it was written 1 day late. So your penalty is basically how many days late you submitted. So this is your penalty over here. That is the number of days you submitted the book
कोडिंग
late.
समझा दे ना, मैं फिर से क्वेश्चन में रीड कर लेता हूँ.
And this is the day on which you return the book. All right. Now in the first question, well, I says how many days you return the book late. Well, I equal to 1 means you return the book late 1 day, and A of I, that is A of 1 is 1, which implies that you return the book on day 1. Similarly, like I equal to 2, you faced a penalty of 2 for returning the book 2 days late, and A of I 2 means that you return the book on day 2. Here, like it would be all 1, 1, 2, 2, 3, 3. So on day 1, you would get a penalty of 1. On day 2, you get a penalty of 2. On day 3, you get a penalty of 3. And adding all these up, like 1 plus 2 plus 3 is 6. And that's like answer for our first test case. Now, if we look at the second test case, that's where like it gets. So if we look at our second test case, it's 1, 1, 2, 2, 3, 3. So our array is 1, 1, 2, 2, sorry, 1, 1, 2, 2, not 3. And if you look at I, what would I be over here? This would correspond to the first index, that's I is 1. This is I is 2, I is 3, and I is 4. Now let's once again draw up our table, like what would be my penalty and on which day was this book submitted? Like how much penalty did this book have and on which day was this book submitted? Now I equal to 1 means that this book had a penalty of 1. It was submitted 1 day late. And the corresponding A of I, 1 means that it was submitted on day 1. I equal to 2 means that it had a penalty of 2, that is it was submitted 2 days late. And the corresponding A of I, that is 1, implies that it was submitted on day 1. Similarly, I equal to 3 means that penalty of 3, and the corresponding A of I was 2, so it was submitted on day 2. And similarly for 4, penalty of 4, so the book was submitted on 2, So the book was submitted 4 days late and it was submitted on day 2. Now the question said that if multiple books were submitted on same day, so you can see that 2 books were submitted on day 2, only the highest penalty would be considered for that day. So over here, even though you have penalties of 1 and 2, only the highest among them would be considered on day 1. So on day 1, you are going to have a penalty of 2, which is maximum of 1 and 2. And these 2 books were also submitted on the same day, that is day 2. So for these 2 books, like the highest among them would be considered. So highest among 3 and 4 is 4. So you would consider the penalty of 4, and 2 plus 4 is basically 6. So 6 would be your answer for the second test case. And for the third test case, like it's likewise similar. So for the third test case, if we just quickly draw the penalty and day chart, like the penalty would be like I equal to 1, 2, 3, and 4. So you would have these penalties, and the day would be 1, 1, 2, 1. So penalty 1 submitted on day 1, penalty 2 submitted on day 1, 3 on day 2, 4 on day 1. Now you could only have a single penalty on day 1. So on day 1, you had penalties 1, 2, and 4. So corresponding to day 1, you have 1, 2, and 4. And the maximum of this is 4. On day 2, you had penalty of 3, and like maximum of just 3 is 3, and 4 plus 3 is 7. So that would be your answer for the third test case. Now, the overall logic is kind of very straightforward. Basically, for each penalty, you maintain some sort of data structure where you, like, if you're getting this penalty on this day, basically penalty of I on day A of I, you either can maintain some sort of data structure where you update the penalty on day A of I to like maximum of what it was previously, or the penalty that you're getting right now. Or otherwise, there is a different approach where you could sort by A of I and I, and basically like if you consider this test case 1, 1, 2, 1, and you have over here like I is 1, 2, 3, and 4, then what you could do is you could maintain, let's just say that you have a map from end to end, and initially like all the days have penalty of 0. So we have day 1 and 2, and we have the penalty. Initially both of them are 0. We see I equal to 1, day equal to 1, update the penalty. I equal to 2, day equal to 2, update the penalty to maximum. I equal to 3, day equal to 2, update the penalty to maximum of what it is, say 3, and penalty is 4, and day equal to 1, update it. And finally we can just calculate the sum of these two. So map of set of end. Second test case was second test case, could you please again? Okay, yeah, right. So for the second test case, if you look at the second test case, yeah, the second test case was your array was 1, 1, 2, 2. All right. What this said was, first you start iterating from I equal to 1, 2, 3, and 4. Your array size is 4. So basically for each corresponding index, what it meant was that you return the book on day 1, that is day A of 1, and you had a penalty of this much. So if you iterate over your array, and this is your array, so your I can be 1, 2, 3, and 4 because the size of your array is 4, and these are your corresponding elements. So what this meant was you return the book on day 1. So A of I implies day. So you return a book on day 1 that had a penalty of 1. Then you return one more book on day 1 that had a penalty of 2. So on day 1, you got 2 books. Okay, so on day 1, you actually had 2 books. The first one had a penalty of 1, and the second one had a penalty of 2. Now, what the question said was, if you read the question over here, when multiple books are returned on the same day, only the highest penalty among those books is counted.
अभी हमारा भी इंटेलिजेंट
Now, what this means is that you had two books on day one and you want to calculate the total penalty that chef is going to face. So according to question, only the highest among these. So highest among these penalties is 2. So you're only going to count penalty of 2 for day one. And then similarly, like if you look at the below two books, like this book was returned on day 2 and it had a penalty of 3. This book was returned on day 2 and it had a penalty of 3. So on day 2, you had this book which was returned with a penalty of 3, and you had this fourth book which was written on day 2 with a penalty of 4. And again, according to question, what is the penalty for day 2? Basically, you're getting penalties for day wise, like each book has a particular penalty. Now on the basis of the books that are received on that day, you assign a penalty to that day. So what is the penalty for day 2? The penalty for day 2 is maximum of these two, which is 4. And then basically you just sum up the penalties for each of the days, and that would be your answer, that is 6. So are you keeping the higher index as penalty? Yes, like basically we want to on this day, if you, so basically if this is the day, on this day, if you get penalties for I equal to 1, 2, 3, and let's just say 7, then your highest index would be counted as the penalty of this day. And yeah, like that's the basic idea. Thanks. Okay. Now moving on to the code for this problem. Okay, so basically like this is the code for taking test cases, and for each test case, first you input the integer n. Then what I've done over here is maintained a map of penalty for each I, like starting from I equal to 1 to n. Now I means that this book is returned with a penalty of I. So starting penalty of 1, 2, 3, all the way up to n. And A of I means the day on which this book was written. Okay. Now what we say over here is the penalty for this day, that is the day A of I, is maximum of what the penalty for this day already is. Like by default, map defaults to 0 or I. And actually, like since we are iterating from 1 to n, we can also like directly just say that penalty of A of I equal to I, because I is strictly increasing, so it would be greater than what it already was. But like, even this works. And then, so basically after the end of this loop, what we have is for each day, what is the maximum penalty for that day? And then we want to calculate the total penalty. So the total penalty would be like you iterate over all the days and the penalties in this map. So for this day, you had a penalty of maximum penalty of P, and you just sum up all these penalties and get your total penalty. Or we can start for looking the first occurrence of num from the end of array and answers position of it. Yes, yeah, you could also do that. And there's like one more way, like this basically this approach was to use some data structure to store these penalties. If you wish to do it without any data structures, like one more way, possible way would be you could have a pair of A of I and I, then create a vector out of it. Like for example, you have 1, 2, 1, and you have I equal to 1, 2, 3, and 4. Then basically like what you could do is sort according to your A of I, like sort your I according to your A of I. That would get you to like 1, 2, 4, and 3, like something like you create an array which is like A of I and I, 1 and 1, 1 and 2, 2 and 3, and 1 and 4. Then you can just sort this and take the like highest I for corresponding day. That would be like something a bit more complicated, but won't use data structures. Can we use unordered map instead of map? Is it better in time complexity? Yes, in most cases, like with hash, you get O of 1 time complexity. I'm not exactly sure if you can iterate over an ordered map in this way, but yeah, like for lookups and updates, if you don't really have any collisions in your kind of code, then it would give a better time complexity. So, all right, like someone has shared their code. Yes, I guess this works too. Okay. Now let's move to the second problem. So the second problem was distinct power. And over here too, like you had a story like in the ancient kingdom of Warriors, basically you had an array of integers n, where a of I represented the power of the ith troop, and all powers in a of I were distinct. And on the basis of these powers, you assigned a rank to each troop. So basically the troop with highest power got rank 1, the troop with lowest power got the rank n. So you had n troops, each with a distinct power. And on basis of these powers, you assign them ranks of 1 to n. And the highest troop got rank n, next rank 2, and so on up to the lowest troop getting a rank of n. And the ranks array would form an array of B. Now, if A was this, then you would get a B of this. Then what we have to do is we have to remove exactly one troop from the array. And when this troop was removed, you would once again calculate the rank array, like you would once again assign the ranks to remaining troops. And on the basis of that, you would get one more array. And we have to find, like, after you remove each of the possible elements, like there are n elements, and if you try to remove each of the elements, how many distinct rank arrays are possible? Okay, so in like simple terms, in the most brute force manner, what you do is you go from 1 to n elements, remove that element, and take the n minus 1 elements, calculate the ranks, and then see how many distinct such arrays you get of the n arrays. And these were the constraints, like t is from 1 to 10 power 4, n is from 2 to 3 times 10 power 5, and a of I is up to 10 power 9, and sum of n over all test cases is at max 3 times 10 power 5. N being 3 times 10 power 5 means that you can't really implement the brute force approach. But let's just go over the sample test cases first. Just a second. Now let's look at the first test case. So in this first test case, our array A was 5, 8, 4, 1. Okay. Now array B, which is the rank array according to our question, would be this. What is the highest powered troop in this array? It is 8. So this will be assigned a rank of 1. We have dealt with that. Now what is the next highest remaining troop in this array? Well, it will be 5. So this will be assigned a rank of 2. What is the next highest remaining troop? It is 4. So that has a rank of 3. And what is the next highest? 1. The last remaining, that has a rank of 4. Okay. Now what the question said was, this was the B for like the rank array for the initial given A. Now what the question said was, you had to remove exactly one element from this array A. So you had 5, 8, 4, 1. Now you could remove any of these 4. Let's just say we start by removing 5. Okay, what happens when you remove 5? When you remove 5, you are left with this array 8, 4, 1. Now let's calculate the rank array for this. Rank array for 841 is, what is the highest rank over here? It is 8, so rank of 1. Next highest 4, rank of 2. Next highest 1, rank of 3. So this is the rank array that you get by removing 5. Oh, outside. So then what's the next element that you can remove? Well, the next element that you can remove is, so you have tried removing 5. Then let's just say that we didn't remove 5, but rather we removed 8. If you remove 8, the array that you get is 5, 4, and 1. Let's calculate the rank array for this. What's the rank array? What's the highest ranked element? Like what's the highest powered element? 5. So this gets a rank of 1, then 4, rank of 2, and then 1, rank of 3. So you see these two arrays are same. So up until now, you only have a single unique rank array. Then next, like what's the next element you can remove? That's 4 over here. So you had 5, 8, 4, and 1. And the next element you can remove is like 4. We have tried removing 5, we have tried removing 8. We can remove 4 now. We'll be left with 5, 8, and 1. Let's calculate the rank array for this. What's the highest? 8, rank of 1. Next highest, 5, rank of 2. And the last one, rank of 3. Now we have got a different rank array. So we have got rank array of 1, 2, 3. Then the next was 1, 2, 3. And this was 2, 1, 3. So we at least have two different rank arrays. So our rank arrays are like we have got 1, 2, 3. Then we have got 2, 1, 3. And then let's try removing the final element. That is, so we have tried removing 5, we have tried removing 8, we have tried removing 4. Now let's try to remove 1. Let's see what happens when we remove 1. So that's 5, 8, 4. And once we remove 1, we get 5, 8, 4. What's the rank array for this? What's the highest rank? 8. Next highest 5. And the last one, 4, that is 3. And you see like this two arrays are same. So we only get two unique arrays, that is 1, 2, 3 and 2, 1, 3. So the answer for the first test case is 2, like we get two unique arrays, and it's 2 over here. This gives TLE. So sorted A is you're sorting it, you're maintaining an order. I think what you are trying to do is, I'm not sure what you're trying to do over here, but I think like this is like two nested for loops. This is going from I equal to 0 to n, and this is going from j equal to 0 to n. So this would overall go to O of n squared. Now O of n squared with 10 power 5, that would be like 10 power 10. And that would TLE, like you could at most go up to like 10 power 8, around 10 power 8 operations with good implementation. So this would like TLE because you have two nested for loops over here. Yeah, I guess I don't really see any break conditions. So yeah. Now, yeah, like that was the first sample test case, and for the remaining two, like we have something similar. Uh, I won't go over these, but yeah, it's like kind of you try to remove each of the elements and see what's the rank array that you get, and try to see like how many different rank arrays that you get. In second test case, you get 4, and in the third, you get 5 different rank arrays. Now, let's try to see. So the most brute force approach to this would of course be that you go from I equal to 1 to n, then try to calculate, like then you just remove a of I and calculate the new rank array. This would take about O of n time, like you could go over all the elements that are not I and try to assign them a rank. And this above loop would also go O of n. So the total time complexity would be O of n squared for the straightforward solution, but our n is like around 10 power 5. So n squared would go to 10 power 10, and you can only have like operations up to 10 power 8 in 1 second. So this won't work. So we have to try something different. So by something different, let's see what's happening over here, like what's happening above over here. So first, let's take the initial rank array that we have. That's, let me see, like, okay, we have this, what was, yeah, our initial A array was 5, 8, 4, 1. Then our initial rank array, that's B, was 1, 2, 1, 3, 4. And what happened after we removed the first element? Well, removing the first element corresponded to like removing this 2. Okay. When you remove this 2, what happens? Okay. The first element remains like this correspond to the highest element. So this is still the highest element. The second highest won't be present because we have removed it. The third highest, now 4 was the third highest and 5 was the second highest, but 5 is no longer. So 4 is going to be third highest. So 3 is going to be converted to a 2. Then this 4 is going to go to 3. Like basically because we removed the second highest, 3 can go to like 3 is now the second highest. So 3 would be updated to 2. And like because 3 is updated to 2, so the third highest is empty. So then 4 can move to its place and be the third highest. So basically when you remove this element, 1 remains highest and it remains as it is. And 3 moves to 2's place, 4 moves to 3's place. Like basically 3 converts to 2 and 4 converts to 3. What happens when you remove the second element? Well, when you remove the second element, the highest place is empty, so there's no one claiming to be highest now. So who is the next person who is highest? 2. So 2 will be converted to 1. Then similarly, like 3 would be converted to 2 and 4 would be converted to 3. So you get a 1, 2, 3. Sir, I made rank array to 2 pointers which are already forward. Can you tell me why? Yeah, like we'll discuss like why this works. And like okay, like this is the basic. So what we did above over here was we tried to remove an element from the array A of I and then we calculated its rank array. Now what we're trying to do right now is let's try to remove the element itself from the rank array that we have calculated from 1 to 4. And once we remove it from this rank array, let's see how the new updated rank array relates to the previous rank array. So basically, if you remove the first element, this gives you 1, 2, 3. And what's happening is, if you remove 2, 1 remains as it is, 2 is removed, 3 converts to 2 and 4 converts to 3. Why does this happen? When you remove 2, the second position was empty. Then who could fill who is the highest person who could fill it? It was the third strongest person. Then since he filled it, like its position remained empty. So who could fill it? Well, the fourth strongest person. So 4 got converted to 3. And if there was fifth, then it would just go on filling and filling. And basically that's what happened here too. And just like, let's go the remaining 2. So you removed this guy. Then 1 is unaffected, 2 is unaffected. But 3 is no longer. So 3's position is empty. Who is going to fill it? 4 is going to fill it. So 4 gets converted to 3. And your final array would look like something like this. So basically like 2, 1 remains as it is, 4 is converted to 3 and 3 is removed. So you have 2, 1 and 3, 2, 1, 3. And finally, let's just try to remove 4. Well, when 4 is removed, no one is affected because 1 is still the highest, 2 is still the second highest, 3 is still the third highest. 4 was removed, but there's no fifth guy, so no one gets updated. And that's like overall what's happening over here. So I hope this what's happening in the rank array is clear. Now, if that's clear, let's see this like what's exactly. So let's just say you have these 6 ranks. When you remove this 4th rank, so let's just say that your n was 6, and when you removed 4, like let's just say that your n was 6, and forget like how your rank array looked like, but let's just say this was your rank array. Okay, now you removed 4. 1, 2, and 3 will remain as it is. So 1 would remain unchanged, 2 would remain unchanged, 3 would remain unchanged. The place of 4, like the fourth strongest person is no one right now. So 5 would move in its place. fifth strongest person is no one right now, so 6 would move in its place. 6 would move in the 5's place and 6 would become 5. Basically, if you remove x, 1, 2, 3 all the way up to x minus 1 remain the same. And from x plus 1 to n, they are converted to x to n minus 1. And finally, like you have an array of n minus 1. Now, the idea in this is that if you actually look at, like, let's try to remove a few elements. So you had an array of size 6, and what happens when you remove the first element? 2 gets converted to 1, 3 gets converted to 2, 4 gets converted to 3, 5 to 4, 6 to 5. What happens when you remove 2? 1 remains as it is, 3 gets converted to 2, 4 gets converted to 3, 5 to 4, 6 to 5. What happens when you remove 3? 1 and 2 remain as it is, 4 gets converted to 3, 5 gets converted to 4, 6 gets converted to 5. Like for last, let's just try to remove 4. 1, 2, and 3 remain as it is, 5 gets converted to 4, and 6 gets converted to 5. Now look at the changes that you get when you remove adjacent elements. Okay, now you removed 1 over here and you removed 2 over here. Look at the remaining array. Like once you removed 2, 3 got converted. Once you removed 1, 3 got converted to 2, 4, 3, 5 to 4, 6 to 5. Okay, and even when you removed 2, all these elements, like after removal, their conversion remains same. Okay, and if you look at this 3 and 4 removal, let me just use a different color. So if you look at this removal from 3 and 4, after removing 3, 1, 2 remained as 1, 2. After removing 4, 1, 2 remained as 1, 2. After removing 3, 5, 4, 5, 6 got converted to 4, 5. And after removing 4, 2, they got converted to 4, 5. So if you removed x, like if you removed x, you had something like 1, 2 all the way up to x minus 1. This is your x plus 1. And this is your x plus 2 all the way up to n. What we are saying is, if you removed x, like x is a bad number, but like, yeah, if you removed x, then this x plus 1 would get converted to x. And these things would remain, like, let's just say they got converted to this will remain same, and this will start from x plus 1 to n. And in the next step, let's say you try to remove x plus 1, then x would remain as it is, and this would remain same. Basically, what we're trying to say is these parts of the array remain same. So when you removed x and when you removed x plus 1, only these two elements are like kind of changing. Like x was removed and x plus 1 was converted to x remained x, and x plus 1 was removed. So what we can do is, like kind of the intuition over here is, since there's a very small change when you go from x to x plus 1, there's a very slight change when you go from x to x plus 1. There's only two variables that are kind of changing. What you can do is, we can try to iterate from I equal to 1 to n and try to remove the element at that rank. So you can try to remove the first ranked element and you would get one array. Then you go to rank 2 and see like what's the change that you get when you try to remove rank 2 compared to 1, and see that do you get a new array. Do you get a new array? Okay. Let's try to see like what I'm saying over here. So consider this test case 1, 1, 2, 2. Over here, what's your rank array? Well, your rank array is no, it's 1, 1, 2, 2. It's 5, 8, 4, 5. 5, 8, 4, 1. 1, 1, 2, 2 was from the last problem. So what's your rank array in this case? Well, your rank array is, what's the highest? It's 8. What's the next highest? 2. Next highest, 4, that's 3. And the final, that will be assigned rank of 4. Okay. Now, what do you do first? Well, you do is you remove a rank of 1. When you remove a rank of 1, 2, 3, and 4 get assigned the previous ranks, like 2 becomes 1, 3 becomes 2, 4 becomes 3. Okay, then when you remove rank of 1, 2, 1, 3, and 4, 1 is removed and you are left with 2, 3, and 4, and each of them will go to their previous elements, that will become 1, 2, 3. And what happens when you remove a rank of 2, like 1, 2, 3, and 4? When you remove 2, 1 remains itself, 3 and 4 get converted to their previous forms. So you had 2, 1, 3, and 4. You remove 2, the array you are left with is 1, 3, and 4. And then 3 and 4 get converted to their previous forms, that's 1, 2, and 3. Okay. Now what happens when you remove rank of 3? That's like these two arrays are same. Okay. Try to see why these two arrays are same. Well, okay, when we removed everything and all things, like 3 and 4 would remain unchanged. Like after you remove everything, like so before update, after removal of 1, your array looked like 2, 3, and 4, and over here it looked like 1, 3, and 4. So 3 and 4, after conversion, 3 and 4 would be same in both of these cases. So only thing where it can change is your 1 and 2, but 2, 2 gets converted to 1 and 1 remains itself. So these two arrays remain same. And what happens when you remove 3? 1 and 2 remain same and 4 becomes 3. And if we look in this array, you remove 3, you get your array 2, 1, and 4. And your previous array after removal was 1, 3, and 4. And after conversion, like 1 and 2 remained the same, but 4 is converted to 3. So this becomes 2, 1, 3. And over here, this became 1, 2, 3. Now, if we just look at what are the things that we are getting, after removal of 2, this gave us the array 1, 3, and 4. And after removal of 3, we got the array 2, 1, and 3. And after conversion, this became 1, 2, and 3. And this became 2, 1, and 3, like this. Sorry, we got, yeah, this was like 2, 1, and 4. For that, this is 2, 1, and 4. And after conversion, like this became 2, 1, and 3. Now, notice one thing, 4 will remain same. Like after conversion, 4 will remain same. 1 will remain same. We are removing 2 and we are removing 3. So these are the only two elements that are going to change. Okay. What's the position of 3 over here and what's the position of 2 over here? Like after removal, what's the position of 3 and what's the position of 2 over here? The position of 3 is like it's at index of 2. Position of 2 is that it's at index of 1. And if you look at like after we just removed position, like after we just removed 1, we got 2, 3, and 4. So after we had just removed 1, we had gotten like 2, 3, and 4, and that 2 got converted to 1, 2, and 3. Now, if you consider removal for I equal to 1 and I equal to 2, you need to consider like you're removing 2 over here, like 1 and 2 are the only indices that are going to change. Then 2 over here is this guy and 1 over here is this guy, and all other elements are like going to remain same. Like after conversion, their values are going to be the same for both of these cases. So what's the index of 2 and what's the index of 1? Basically, like what we are saying is, if you remove x and if you remove x plus 1, then after the whole like removal, only x or x plus 1, the things that you have in array, only x and x plus 1, they are like going to kind of change, they are going to have change in values, and all the other elements like this 3 and 4 and these 3 and 4 over here, after like the complete conversion, this 3 and 4 got converted to 2 and 3 over here, this 3 and 4 2 got converted to 2 and 3 over here. So these are the only things that are going to change in the array. And if we compare what indices they are present on, so this is present on index 1 and this is present on index 2. Over here, you tried removing 2 and 3. So 3 over here is present at index 2 and 2 over here is present at index 1. Basically, like we are trying to track the change. Like when we removed x, this was it, and when we tried to remove x plus 1, this was it. So x plus 1 was present in this case, but it's not present in this case. and x was present in this case, but it's not present in this case. So we are trying to track the change of how it occurred. Okay. And like what we are saying is, so x plus 1 existed at some index I, and so first like we remove x, and after that we get some array. Then x plus 1 existed at some index I, and after conversion it got converted to uh, like x. Then we try remove I x plus 1. Now x plus 1 is removed, and x remains at some index j, and it just remains at index j. Now the thing is, if this I and this j is same, like if you look at it, like if x is over here and there's some element in between, and you have x plus 1 over here, and after removing x, you would have this some element, and to its right you would get x, because x plus 1 would get converted to x to fill the position of x. And if you have this some element over here and x plus 1, once you remove x plus 1, x would remain to the left of this element. Basically, like what this points to is x and x plus 1, like when you remove x and when you remove x plus 1, the arrays will be same only if x and x plus 1 are adjacent. If there's any element that is between these two, then you would basically like have x's to the left of this guy and x's to the right of this guy in the first case, in the second case, something like this. So basically what we're trying to say is, if x and x plus 1 are adjacent in the initial rank array, then removing x and removing x plus 1 will generate the same array. Otherwise, if there's some element in between them, so if there's some element in between x and x plus 1, when you remove x, this will generate this array, and when you remove x plus 1, this will generate this array. So in between these two arrays, like x was to the right of this element in this array, x was to the left of this element in this array. So overall, like you have a different arrays, and we can just use this fact to check. And I think this is also like how your solution works over here. You're basically I guess you're trying to check if two ranks are adjacent. Like let's just go over the test case once. So just for clarity, 85841, your rank array would like 2134. Now 1 and 2 are adjacent. So after removal, like if you remove 2, 1 would be here. If you remove 1, 2 would remain here and 2 would get converted to 1. So 1 would always remain at this place, and 3 and 4 would like get converted to 2 and 3. So it always get array 1, 2, 3. Now that's if you try to remove 3, well, when you remove, sorry, if you try to remove 2, well, your next 2 will be over here. But if you try to remove 3, your 2 would be over here. So in this case, like 2 is to the right of 1. In this case, 2 is to the left of 1. So basically, since 2 and 3 are not adjacent, removing 3 would lead to a different array than removing 2. And like, so for 3 and 4, if you remove 3, then 4 would get converted to 3. If you remove 4, then 3 would remain at 3. So 3 would basically be at this index no matter which one you remove. So it would be same. And basically like that's the overall idea. And if you go over the code, this is taking test cases, and yeah, this is the code. So first take the number of integers, then we input the array. And like this part is basically we are sorting the whole thing, and we are calculating the index of each rank. So for rank, the index the element at this index has this rank. Basically we are sorting by a of I, and we are saying that the index of 0, like I'm using 0 based indexing, is at this index. And like initially we have a res of 1. Basically if you remove the rank 1 element, you get 1 array, so you at least have an answer of 1. Then starting from rank 2, that is in 0 based indexing, 1 to n minus 1, if the previous rank and the current rank aren't adjacent, like the absolute value of difference between their positions is greater than 1, then you will get a different array when you remove this I. Otherwise, you would get the same array, and basically you increment your answer in this case. So like that's the overall. So which topic does this come under again? This would come under, I'm not exactly sure which topic this would come under, but yeah, I guess you could call it greedy. Yes, I guess I'm not exactly sure if you would call it greedy, but more like implementation wise, you're basically trying to see what's the difference that's occurring when you basically you have been given n operations and you're trying to establish a relationship between these n operations and seeing difference, like this is my first operations, this is my second, third, fourth, all the way up to n. What's the difference between 1 and 2? What's the difference between 2 and 3, and so on up to n? So that's what you're trying to do over here. So I'm not exactly sure which topic this would come under. You could say it's greedy, but more like implementation. Yeah, ad hoc type. This was harder than D. Yes, somewhat harder than D. And finally, like there's one more part where you would also have to prove, like if you really want to go into this rigorously, like this is different. Like let's just say that 1 and 2 are at different indices. So this leads to some array of type say 1. This leads to type 2 array. This leads to type 3 array. And if you like really want to go into this rigorously, then you would also have to find some way to prove that 1 and 3 are not the same in any condition. You could do that with like something like in case of 1, 2, 3 and up to n are changing. In case of 2, 3 to n are changing and 1 remains the same. And in case of 3, like next guys are changing and 1, 2 remains over here, it remains the same. So like basically you could just play with the index a bit and prove this. It would be slightly complicated. So yeah, which question is this? So this is question C and distinct power. No, this is question B, sorry, not C, the distinct power. And let's move to the third question. So let's move to the question C, that's costly permutations. Like, are there any doubts? Let's see, I think this is, yeah, right. So now let's move to the problem C, that's costly permutations. In this problem, like every Christmas, chef gives you a gift of permutation of size n. Then for each index in this permutation, you calculate a value v of I. And this value is calculated on basis of this process. Basically, you start at index I, and let's just say that your current index is k, and then you have your permutations point to p of k, and you go to p of k, and you continue this until your like index returns to I. Basically, like if you look at this array, you start with index 1. Well, index 1 says 3, so you go to index 3. Index is 3 says 5, so you go to index 5. Index 5 says 1, so you have returned to your index 1. And this in total took you 4 steps. So you're, no, like 3 steps, like 1, 1 to 5, 5 to 1, 1 to 3. So 3 steps. So your value over 1 is 3. And chef could perform the following operations. Like basically what he could do is he could swap elements and at I and j, and the cost of this swap was v of I plus v of j. And after he swapped these values, the values of v of I and v of j would be updated, and some others too. And chef's goal was to transform the permutation to achieve maximum possible sum of values, that's summation of v of I up to n. And he wanted to do this while like requiring minimum cost. And that was the overall problem. So let's look at the sample test cases. Okay, like you didn't get the B question. Is that it? Okay, is there any doubt in the B question? Okay, the solution part of the code. All right. So look, what we are doing basically over here is we are sorting our indices by A of I. So if I were to just tell you, so let's forget about C, go to B, and if we go over this sample test case, so I'll just dry run through this sample test case. So this is 8541. Okay. Now first thing we do is we tie them with basically like the whole thing that this part of the code is doing is we are basically just trying to iterate, assign, get index of each of these, like 5 as index of 1, 8 as index of 2, 4 as index of 3, and 1 as index of 4. So index wise. Okay. Then what we do is we sort according to this A. When you sort according to this A, like I have sorted in ascending order, you could sort in descending order, anyways works. Like once you sort this array, you get the array 1, 4, 5, and 8. And what were the previous corresponding indices? Well, the previous corresponding index, 1 was at index of 4, then 4 was at index of 3, 5 is at index of 1, and 8 is at index of 2. So like a better thing would be to basically say sort them in reverse order if you really want to maintain with what we have. But I have sorted them in ascending order and this works too. And now basically what you say is, well, now since we have sorted, the rank 1 is 8. So this has rank of 1, this has rank of 2, this has rank of 3, and this has rank of 4. Now once you have sorted, basically what our solution said was, once you remove this rank 1 from your array and you get a new rank, a new array, and you try to remove rank 2 from your array and you get some other array, these two arrays are different if these two guys are not adjacent in this initial array. Now if these two guys are not adjacent, then the difference between like their absolute value, if these two guys are adjacent, like what happens when 1 and 2 are adjacent? Well, if 1 lies at some I, then 2 is going to lie at some I plus 1, or 1 can lie at some I plus 1 and 2 can lie at I. So in this case we say that they are adjacent, and if you look, this basically says that the absolute value of their indices I minus j has to be less than or like equal to 1, strictly equal to 1, because they can't lie at same index. So, and if they are, if this I minus j is strictly greater than 1, that is to say that 1 lies somewhere over here and 2 lies somewhere over here. So this is the index of 1 and this is the index of 2. If this is strictly greater than 1, then they are not adjacent and you will get a different array when you remove 2. So like what we're trying to do over here is, what's the index of uh, the what does the index, like what's the index of element that has this rank? Okay, like based on like how I have coded, it would be a bit different, but so this was your test case. Then according to this is your rank. So your ranks would be 1, 2, 3, and 4. Now your index would be, what is the index of element with rank 1? It's 1. What's the index of element with rank 2? So 2 is at this, so this has index of 1. So sorry, what's the index of element with rank 1? So the element with rank 1 is this. So this is the element with rank 1. It's at index of 2. Basically, this is 1, 2, 3, and 4. So the index of rank 1 is 2. What's the index of element with rank 2? The element with rank 2 is 5. So index of 5 is 1. Then what's the index of element with rank 3? Rank 3 is this, it is 4. So index of 4 is 3. And what's the index of element with rank 4? the rank 4 element is 1 and 1 is at index of 4. Okay. Now what we are saying is you remove the rank 1 and you get some array. Then you remove rank 2 and then you get some b. These two are not the same if 1 and 2 are not adjacent. Like this b will be different if 1 and 2 is not adjacent. So 1 is over here and 2 is over here. So they are adjacent. What does this mean in terms of your indices? In terms of your indices, it means that this is 2 and this is 1. Like basically this, the difference between these is either plus or minus 1. Then what, like basically this represents the index of rank 1, this represents the index of rank 2. Now you got some array when you removed the element at index, like the rank 2 element. What happens when you try to remove the rank 3 element? Is it different than 2? Are the rank 2 and rank 3 elements different? Well, it lies at 1 and this lies at 3. So 1 is over here, 3 is over here. So there is going to be this element 1 in between. And basically, so these are not adjacent, these are not adjacent. And you could also say in terms of indices, like the difference of their indices is the absolute value of difference is 2, which is greater than 1. So these are not adjacent. So this is going to give us a new array, a different B array. That's what this part says. Basically, here we calculate what's the index of each of the ranks. Then initially we say that our res is 1. This means that we remove the element with rank of 1 and then we get some array. Then starting from I equal to 1, basically we are using zero-based indexing. So I equal to 1, take it I plus 1. So starting from index 2 to n is the array that I get, the B array that I get by removing the I, and the B array that I get that by removing I minus 1, are they different? When will they be different? They'll be different if I and I minus 1 is are not adjacent. If they are adjacent, then basically both of them will end up at the same index. So if they're not adjacent, then I'll get a new array. Since I'll get a new array, so I have a new array to my answer. I want to calculate number of arrays. If I have new array, I'll increment my answer. Like that's the overall idea. Okay. All right. Now let's move to the my third question. Final one. So yeah, I guess we discussed the third question, but I'll go over the test cases because I guess that would be simpler. So right. Now, what this question said was you had this permutation. So let's take the first permutation. Your P is 2, 3, and 1, and your I would be like the indices, corresponding indices would be 1, 2, and 3. Now, what this said was we had a value for each index. Let's try to calculate the value for 1. Well, the value for 1 said that you start at 1. Okay. From 1, what is the P of 1? P of 1 is 2. So you go to 2. So you went to 2. Now you started at 1, you're at 2. From 2, you go to 3. Like, what's the P of 3? It's P of 2. P of 2 is 3. So you were at 1. 1 said that go to 2. So you came at 2. 2 said that go to 3. So you came to 3. And 3 said that, so you came to 3 and P of 3 is 1. So 3 basically says that go back to 1. And basically it took you 1, 2, and 3 moves to get back to 1. So this was your first move, this was your second move, and this was your third move. So value of 1 is 3. Then we said that 1, 2, and 2, 3, and 1. You will similarly calculate the value for 2, 3, and 1. Sorry, for 2, you start at 2. 2 says that go to 3, so you go to third index. 3 says that go to index 1, so you go over here. And finally, 2 says that go to index 1, so you have arrived at your index 1. So if you look at it, you're going to 2, from 2 to 3, from 3 you're going to 1, and from 1 you're going back to 2. So you took 1, 2, and 3 operations. So the value of 2 is again 3. And similarly, like value of 3 would be 3. And in the first test case, like what we have to do is we have to maximize these values for I equal to 1 to n. And in the first test case, like this is already the maximum. So you didn't really have to do any operations in the first test case. It was 0. For the second test case, this would be slightly better for understanding. So now if you look at the second test case, the second test case said that your P array was 4, 1, 3, and 2. And the indices, corresponding indices like 1, 2, 3, and 4. Now, for now, what I'll do is I'll just say that this index points to this. So basically, if you are at I, it says that go to 4. If you are at 2, it says go to 1. If you are at 3, it says go to 3. And if you are at 4, it says go to 2. Now, if you basically start, so let's try to calculate value of 1. You start at 1. 1 says go to 4, so you go to 4. 4 says go to 2, so you go to 2. 2 says go to 1, so you go to 1. And like you started with 1, you have arrived at 1, and you took 1, 2, and 3 moves. So the value of this 1 is 3. Then you start, like similarly for 2, you could just go from 2 to 1, then 1 to 4. Like basically, if you start at 2, 2 says go to 1, 1 says go to 4, and 4 says go to 2. You arrived at 2, value of 2 is 3. Similarly for 4, like value would be 3. And for 3, 3 says go to 3 again. So you just need to do one move and you are at 3 again. So value of 3 is 1. And what this said was you could swap, like now values are 3, 3, 3, and 1. And we want to maximize the sum of these. And the question said that you could swap two values. So let's just say that we swap the 3 and 4. Now swapping 3 and 4 takes v3 plus v4 sum. So v3 is 1 and v4 is 3. So it takes 3 plus 1, that is 4. The cost is 4. Cost of swapping 3 and 4 is 1 plus 3, that is v3 and v4, which is 4. And once you swap 3 and 4, like basically you are at 4, 1, 2, and 3, and 1, 2, 3, 4. Now, if you look at what's happening over here is you start at 1, 1 says go to 4, you go to 4, 4 says go to 3, so you go to 3, 3 says go to 2, so you go to 2, 2 says go to 1, and you are at 1. Basically, like you have ended up at 1. So you took 1, 2, 3, and 4 operations. All right, like V1 is 4, and not 1, 4. And similarly, like you could calculate, and all the V3 and V4, all of them would be 4. And you can also kind of prove that this is the maximum value. And what's the cost of the operation that we did? Well, we did an operation with the cost of 4. And the answer is 4 over here. So that was the sample test case. And let's see what's actually happening over here. Okay, so if you look at your permutation, that's 4, 1, 3, 2, 4, 1, 3, and 2. And if you look at your indices 1, 2, 3, and 4, basically one operation kind of corresponds to going from one index to other index. And you could kind of imagine this as a graph. So a graph where each index is a node. Imagine that each index is a node. All right. And like each operation, you can imagine each operation as a directed edge. So you have 4 nodes in this case, like you have 1, 2, 3, 4. So you have 4 nodes, and you go from, like I equal to 1 is 4 implies that you go from 1 to 4. When you are at 1, you go to 4. When you are at 4, you go to 2. When you are at 2, you go to 1. Like when you are at 2, you go back to 1. And 3, when you are at 3, you just go to 3. Okay. And now if you look at it, the v of I, the value of 1, what's it? Well, I'll use a different color. You start at 1, you do one operation, go to 4, you do one more operation, go to 2, and then you cycle back to 1. So basically it's the number of edges in this cycle, or even the number of nodes, because like each node has exactly one out degree. You can actually kind of prove that all the cycles in this graph will look something like this. So it won't be a very complicated graph with two out. So there's no node with two out degrees. Like there's no node with two outgoing edges. All nodes have a single outgoing edge. So you'll always have a graph of this form where you start over here, and, right, like at worst something like this. So no, in fact, since this is permutation, like each node has at most one out degree and at most one in degree. So you can actually prove that this complete graph would be composed of cycles of this form. So you'd never actually have something like this, because this has an in degree of 2, or something like this has an out degree of 2. So both of these cases would be not possible. Basically you would always find a graph of this form. Is this like the longest cycle? Not the longest cycle, like you have to construct the longest cycle. Okay, so if you like kind of break down this your all nodes into these graphs, if you look at what's the value of 1, you start at 1, iterate 1 edge, 2 edge, 3 edge, and you're back at 1. So basically value of 1 is the length of the cycle, like the number of nodes or edges in this cycle, that's 3. Similarly for 4, next, let's try to calculate 4. For 4, you start over here, 1 edge, 2 edge, and 3 edge, and you're back at 4. So according to our question, the value of 4 would be through uh, 3. And similarly for 2, like you start here, then you go to 1, one operation, go to 4, one operation, and come like you're back to 2 after the third operation. This would be 3. And for 3, your answer would be 1, because you start at 3, do one operation, and you're back at 3. Basically, what you're saying is value of I equal to the number of nodes or even edges, because in this case, each cycle will have same number of nodes and edges in the cycle containing I. Okay. And we have to maximize this sum. So we have to maximize this sum, summation of V of I from I equal to 1 to n. Now think about it. What can be the maximum value of V of I? What is max V of I? Okay. What is the maximum value of V of I? So we want to maximize this. So obviously we want to maximize each of the V of I. What's the maximum value of V of I? Now, any doubts? All number nodes, right? All the nodes in the cycle. So in the like best case, like just consider one situation over here, like you go from 1 to 2, 2 to 3, and 3 to 4, all the way up to say you have n nodes, and finally from n you can just come back to, and like this would correspond to the permutation 2, 3, 4, all the way up to n, and finally 1. Basically this is 1 goes to 2, 2 goes to 3, n minus 1 goes to n, and finally n goes to 1. So in this case, like we know from above here, like intuitively you can know that each node is going to have the same value, that's the number of nodes in this cycle. So each of the nodes in this kind of cycle, like there are all the nodes are in the same cycle, number of nodes in the cycle is n, and so V of I is going to be equal to n for each of these nodes. So like each node I is in cycle with n nodes. So V of I is going to be n for all I. Then your summation of V of I is going to be like summation of n from I equal to 1 to n. That's going to be n squared. And you can see that this is the maximum possible value that you can achieve. V of I can never exceed n. That this can never happen because this means that you have cycle of n plus 1 nodes and there are only n nodes. So V of I can be at max n and there are exactly n nodes. So n squared is the maximum that you can achieve. Basically, you are going to achieve maximum when all nodes are connected in a cycle. And now the question is, so you have something of this form, 1, 2, and 3. So if every, like, initially, if you look at the initial, like the first test case, yeah, like this was the first test case. Over here, one side go to 2, two side go to 3, and 3 side go to 1. All nodes were in a single cycle, so you already had the maximum and there was nothing else to do. But now if you come back to our second test case, we come to our second test case, I think it's different. In our second test case, like we have 4, 1, 3, 2. So 1 goes to 4, 4 goes to 2, and 2 goes to 1, and 3 is over here. And now somehow we want to combine all these nodes into a single cycle. All have maximum. Yeah, right. 3, 1, 4, 1, right, all have a maximum because all of these permutations go into one cycle. Now, what's the operation that we have? Like basically what we have to do is we have to find some way to merge these two cycles. And what's the operation we have? We can swap two nodes. All right, we can swap two nodes. Now what happens when you swap the nodes? Like what happens in terms of this graph? Like what happens when you swap two nodes? Okay, what does this outgoing edge mean? This means that P of 1 equal to 4. Okay. And what does this edge mean? Like 3 pointing to itself. It means that P of 3 is equal to 3. When you swap 1 and 3, P of 1 is going to be like before swap. So I'll just draw it over here. So 1 points to 4, 4 points to 2, and 2 points to this, and 3 points to itself. This edge means that P of 1 is equal to 4, and this edge from 3 to itself means that P of 3 is equal to 3. This means that 3 points to 3 itself and 1 points to 4. When you swap 1 and 3, P of 1 is going to equal to 3 and P of 3 is going to equal to 4. Like initially P of 1 was 4, now P of 3 became 4, and here P of 3 was 3, now P of 1 became 3. Okay. Now P of 1 becomes 3, it means that you have torn off this edge and pointed it over here, and you have turned off this edge and you have pointed it over here. If you look at what happened, 1 now points to 3 and 3 now points to 4, and 4 points to 2 and 2 still points to 1. So this part remains same, but 1 and 3 have basically exchanged the edges that they are pointing to. And in fact, if you look at it in any other sense too, so even if you had a larger cycle, so let's just say you had these two cycles, 1, 2, 3, and 4, 5, and 6. There's no test case in the sample as such, but let's just say you had some permutation that generated these two cycles. And what happens when you swap nodes, say 3 and 4? Okay, what happens when you swap nodes 3 and 4? Initially 3 used to point to 1, and this basically meant that P of 3 was 1, and 4 used to point to 5, this meant that P of 4 was 5. But now after swap, P of 3 is going to be 5 and P of 4 is going to equal to 1, right? What would this mean? So 1, 2, and 3, and 4, 5, and 6. 1 and 2 would still point where they were, 5 and 6 would still point where they were. Now 3 would point over here and 4 would point over here. Basically, you have merged these cycles. And if there were only 6 nodes, like this is all you wanted. If there were more than 6 nodes, you would have more, uh, like more nodes to swap, more operations to do. But the observation is that, and this is like a fairly common observation if you deal with permutations and cycles and permutations basically. If you swap 2 nodes in different cycles, then you merge these cycles. So over here, what we did was we swapped a node that was in this cycle and a node that was in this cycle, and that basically led us to a new merged cycle there. So we had 2 cycles of length 3, and now we have a single large cycle of length 6. And so this is the only observation that would help us solve it. But there's also a counter to this observation that, like, if you swap nodes in same cycle, it breaks the cycle. Like it creates 2 new cycles. For example, if you have 1 points to 2, points to 3, that points to 4, and that points to 1. And let's just say that you swapped 1 and 3. 1 used to point to 2, but now it's going to point to 4. So 1 now points to 4, and 4 points to 1, and 2 points to 3, that remains it's as it is. 3 used to point to 4, but now 3 would point to 2 that 1 pointed to. We aren't really using it over here, but it's like something that you would encounter fairly common when, like, it's something related to cycles in a permutation. That's like maybe you would end up using it in some other problem, but in this problem we are just using this observation that if you swap 2 nodes that are in different cycle, you merge the cycles that these nodes are in, and this is like the alternate observation. So yeah, right. Now you have way to merge the cycles. You can merge the cycles. Okay. So you can merge the cycles. Now, the sample test case was simple because you just had 2 cycles. So you knew, like, you just had 1, 4, 2, and you had this 3. And this cycle had a length of 3, and this cycle had a length of 1. So you could just pick up any 2 nodes, swap them, and get a cycle of length 4. And the total cost would be 3 plus 1, that is 4 itself. So you get a total cost of 4. Now in this case, it's very like simple. But what happens if you have many cycles? Like let's just say you have multiple cycles. You have 1 cycle of length 3, 1 cycle of length 3, 1 cycle of length 1, and 1 cycle of length 1. I did DFS and stored the size of component, but I was wrongly adding their length to answer. Um, Merging and yeah, right. The question indeed boils down to merging all the cycles to the like largest cycle with minimum cost. Can we swap 2 nodes in 2 cycles to merge it? Yeah, right. Like that's the observation. And now what do you do when you have like many cycles? Okay, you have 4 cycles over here. So like this is 4 cycles, and this basically corresponds to something like 1, 2, 3, 4, 5, 6, and maybe 7 pointing to itself and 8 pointing to itself. You could imagine a graph that like a permutation that forms a graph something like this, and that would have these 4 cycles. Like you have 3, 3, 1, 1. Now, what I'm saying over here is now this can like sound out of nowhere, but basically, if you just go on greedily merging all these cycles, like what's the cost of merging 2 cycles? If you merge this cycle with length 1 and length 1, the cost is 1 plus 1, that is 2, and you would end up with cycles 2, 3, and 3. Like basically you merge the cycles with the least 2 length. Then you have 2 and 3, like find the cycle with the least 2 length, and then the cost of merging these would be 2 plus 3 equal to 5, and you have 5 and 3. Then the remaining 2 is like 5 plus 3 equal to 8. That would be your cost, and you finally just merge these two to get a cycle with length 8. That's your optimal value, and your total cost would be like 2 plus 5 plus 8. That would be 15, I guess. So what I'm saying is this greedy approach of like find min 2 cycles and merge them, min to like minimum on the basis of their length. This will work in this case. Why? Well, like a good question is, why will this work? Now, if you actually look at it, like we are already dealing with a graph, so this may sound a little more like complicated, but what you are doing over here is, in a sense, you're calculating the minimum spanning tree. Like why minimum spanning tree? Like if you don't know about minimum spanning tree, like this is just like intuitively what you're doing over here is you take all these three, you take all the cycles that you have, find the minimum cycles with like the least two cycles with the least, like two cycles with the least length, and merge them, put them back into the cycles. Once you are back into cycles, then once again find the two cycles with least length, merge them again, find two cycles with least length again, merge them again, and all the way up to you get to one cycle. This is basically a greedy approach. Why does this work? If you kind of see what we are trying to do over here is, we are in a sense constructing a MST, like to some degree you could say it's a MST. Or if you want like a better argument, it would be like, is if there's some point, if there's some point at which like you have x, y, and z, and x and y are minimum, and let's just say that z is greater than y, there's one solution where you do x plus y and where you leave z at it as it is, and there's other solution where you do x plus z and say that you leave y as it is. Like after a certain number of operations, and a certain number of operations like, and basically like after this operation you do everything else in same fashion over here. Like whatever operations that you do on x plus y, you do the same operations on x plus z. Whatever operations that you do on z, you do on y. The kind of, what I should say, the question is like, will this approach ever be like, will this approach ever beat this approach? Like will this ever be less than this? So you could in a sense prove this. Like the proof would be a bit like lengthy if I will really go into it rigorously, but basically if x plus y and x plus z is greater than this y and z, then this will always have less number of operations than this. And once you have less number of operations than this, then you can kind of argue on the basis of that x plus y is less than x plus z, and z may be greater than y, but the total number of operations that you do on x plus y is more than the total number of operations that you do on z. So the difference between these, like this is kind of minus delta and this is kind of plus delta, so the difference would be greater in this case. So you could argue on that, but basically like the overall idea is that the greedy approach works. Intuitively it would be that you just go on merging the two cycles with minimum length, and that works. You can also kind of think of it in terms of a MST, like you're trying to build a MST, but I'm not sure how you would define the edges and all those things. But yeah, like base, okay, someone has shared their code. If visited of I is not DFS temporary, visited of I. Okay, this DFS is, please tell me if my approach is correct and how to sum. In your approach, I guess you're calculating the cycles over here. So yeah, I guess this is correct for most part. Okay, and this is correct too. Once dot begin. Okay, how to sum? Okay, So we'll see that over here. So your approach for calculating the cycles is correct actually in this code. So we'll see how to sum over here. Now, what is there? Like first we take the input, and below is like we take input for test cases. Here we take the input first, how many numbers there are. Then we take input the permutation. I have used zero based indexing, so like instead of 1 to n, I'm converting it into 0 to n minus 1. Then we just like rather than maintaining it in an array, I'm maintaining it in a priority queue named cycles. And basically this whole part converts this into a minimum priority queue. So the element at top would be the least element. And we start with a visited array. Now we iterate from 0 to n minus 1. That's all the nodes there are. If this node is not visited, we just say that the cycle length is 0 and just go on like kind of iterating all the possible, what you could say, nodes that you can reach from this. So like this is like kind of iterating over the whole cycle, go from 1 to 4, 4 to 2, 2 to, and once you're back at 1, then you know that you have completed the whole cycle and you have the complete cycle length. And we just push these all cycle lengths into our priority queue. Then our res is 0. And while our cycle size is greater than 1, so there are at least 2 cycles, take the cycle with least length, then remove it from the cycles. Take the cycle with least length from the remaining cycles, basically the 2 cycles with the least lengths. Operate on these 2 cycles, like choose any of their nodes and basically swap them. That would cost you a plus b, length of cycle 1 plus length of cycle 2. Add that to your answer. And finally, just push this thing. Like you get a new cycle with length a plus b, insert that into your like whatever cycles you have right now, and continue this operation until you have exactly 1 cycle remaining. As long as you have at least 2 cycles, you just go on removing the 2 cycles with least length, operate on them. That will cost us this much, and we get a new cycle with a plus b cost, like a plus b length, and we just go on doing this thing until we have exactly 1 cycle remaining. And finally we just output our result. So what is the benefit over vector? I am not used to priority queue in solving so like the priority queue over vector is that, let's just say that your cycles were something like 2 to 5. Like basic thing is like if you try to sum over here, so okay, so in a vector, what could happen is you merge these two things. Okay, this became 4. Then you merge this 4 with 2. This became 6. And next you had 5, 5, 5, 5. Okay, so you have merged these two. You got a 4. Then this 4 was still the second minimum, so you merged it with 2, and you have got a 6. But now moving ahead, you don't really need to deal with this 6 anymore. You have to actually merge these 5 and 5. That would give you a cycle of length 10. The next you have to merge these 5 and 5. That would give you a cycle length of 10. And then after that you have to merge this 6 and 10. That would give you 16 and finally 26. The problem is that you're not really actually operating on this thing linearly. So there's nothing like merge this first, then merge this, then merge this, and so on and so forth. One possible way, like you could maybe binary search on it or something, but I mean overall it would be very difficult to, like, you merge these two things and you get a new cycle. Where exactly do you insert it in your array? And after you insert it, overall insertion is a costly operation. And like how exactly do you update your array to kind of get the next two minimum elements in a better time complexity? With priority queue, what you can do is you kind of have this 2 2 2 5 5 5, and let's just say more 5. And with priority queue, what you can do is, there are just two twos. With priority queue, what you can just do is, okay, priority queue, give me the first minimum, remove it, give me the second minimum, remove it. Now this is your remaining priority queue. Operate on them, you get a 4. Maybe we actually had third 2. So operate on them, you get a 4 and insert it into priority queue. Now your priority queue would in big O of log n time update itself so that 2 is over here, 4 is over here, 5, 5, 5, 5. It basically uses something called the max heap, and with the modifications we have a min priority queue, so it would be a min, and then you could get the next two elements from the priority queue. Then your priority queue would be limited to this, operate on them, get a 6, then you would have 5, 5, and you would insert it in big O of log n, and like this would just go on, so on and so forth. Basically the reason why we can't use array is you like there's no linear form of operations that you're doing. Okay, so that was problem 3, and let's move to the fourth problem. Are there any doubts for problem 3? Okay. If there are any doubts to put them in the chat. So let's move to the fourth problem. The fourth problem, divisors array, easy version, and there's the next problem is the difficult version of this. Both of them are pretty similar, just that the constraints on m and a of I are different in both the cases. This problem says that chef has received a math assignment, and basically we are given an array of size n and a positive integer m, and we have to perform these following steps. First, we create an array b of I equal to a of I into m factorial. M factorial basically 1 into 2 into all the way up to m. So multiply integers from 1 to m. And then for each element in the array b, we calculate f of b of I. F of x is the number of divisors of the number x. That's what f is defined as. And like since f can be large, we had to calculate it modulo 1e9 plus like 10 raised to power 9 plus 7. And yeah, like basically this is the definition of b of I, and we have to calculate f of b of I. And the test cases. So let's look at the sample test case. And right, like starting from over here, like this problem, the next, which is a hard version, and the final problem, all of them are based on number theory. So like the last two problems are more or less very heavily dependent on number theory. So that's like one thing. Over here, we are given n equal to 3, this, m equal to 3, the second number, and our a is 1, 2, and 3. Now, we have said that we have to construct new array b of I, which is m factorial into a of I. What's m factorial over here? M is 3, so it's 3 factorial, that is 1 into 2 into 3, that is 3 to the 6. And what's our a of I? Our a is 1, 2, 3, and we multiply that by 3 factorial, that is 6, to get our new array b. So 6 1 is 6, 6 2 is 12, and 6 3 is 18. Okay. What are the divisors of 6? 6 is divisible by 1, 2, 3, and 6. So you have 4 divisors for 6. What are divisors of 12? 12 is divisible by 1, 2, 3. Then you have 4 is a 12, 6 2 is a 12, and 12 ones are 12. So you have 1, 2, 3, 4, 5, 6 divisors for 12. What are the divisors of 18? 18 is divisible by 1, and 9 2 is 18, so 2. 6 3 is 18, so 3. Then 6 3 is 18, so 6 also. Then you have 9 2 is 18, and finally 18 1 is 18. So you have 3 and 3, 6 divisors for 18 too. And basically like you have to calculate this part like 4 6 6, the number of divisors, and yeah, that was your answer. So 4 6 6. We can go like p1 plus q1 in n factorial into a of I. Yeah, right. So that's the idea. So whenever like if So this function f of x is basically the number of divisors of x, and there were like two parts to the problem. First is, how do you calculate f of x efficiently, of course. And the next part was, if you can calculate f of x, and we would see like for that we have to factorize x. Factorize means basically we have to get the prime factors of x. And for a of I, we can do that easily. But m factorial, since m is like less than equal to 100, that would have been difficult. So the next part of the problem was, how do you like how do you find prime factors of m factorial, find all the prime factors of m factorial. So like these were the two parts of it. The part one was, how do you represent this f of x efficiently, like how do you factorize, like how do you find f of x efficiently given some number x. And the second part was, how do you find the prime factors of m factorial. So let's just go over the first part, like first things first. And so let's try to see like f of 12. Let's try to calculate f of 12. Okay. First is like, what's 12? 12 is 3 to the like 6 to the 12. So it's 2 into 3 squared, 2 raised to power 1 and 3 raised to power 1. What are the divisors of 12? It's 1, 2, 6 to the 12, 4 to the 12, 4 to the 12, and you have no, you also have 6 to the 12, and you have 12 itself. So you have total 6 divisors. Okay. And in terms of primes, like usually whenever it's primes, so you have divisors. So you have 12 is 2 raised to power 1 and 3, sorry, it's 2 squared and 3 raised to power 1. Right. So it's 2 squared and 3 raised to power 1, basically 4 into 3. And so let's look at what these divisors look like. So you have divisors 1, 3, 4, 6, and 12. 1 is 2 raised to power 0 into 3 raised to power 0. 2 is 2 raised to power 1 into 3 raised to power 0. 3 is 2 raised to power 0 into 3 raised to power 1. This is 2 raised to power 2 into 3 raised to power 0. And this is 2 raised to power 1, 3 raised to power 1. And this is basically everything that we have. Now, if you kind of look at it, what are your divisors? So 1 is 2 raised to power 0 into 3 raised to power 0. Then you go from 2 raised to power 1 and 3 raised to power 0. Then you can go to 2 raised to power 2 and 3 raised to power 0. Then this 0 goes to 1, and you again have like 2 raised to power 0, 1, and 2 over here. Now, if you look at it, like 12 is 2 raised to power 2 square into 3 raised to power 1. If you ever have something like 8, that is 2 raised to power 3, then this can never, like 8 can never divide 12, because 3 is greater than 2. So if you try to divide it, this would like cancel out and leave a 2 behind, and 2 can, like 2 is a prime number, so it's never going to divide another prime number other than 2. So basically, like, what's the degree of freedom you have over here? So the power of 2 can be between 0 to 2, and the power of 3 can be between 0 to 1. So basically you have 2 plus 1 choices over here, into you have 1 plus 1 choices over here. Basically you have 3 into 2, that is 6 choices over here, and each of these 6 choices correspond to a divisor. And like the overall idea over here is that to calculate f of x, let's just say that you can represent x as, say, prime 1 into some quotient 1, prime 2 into some quotient 2, so on and so forth. Let's just say it has k prime factors and you have q quotients. Then your f of x would be q1 plus 1 plus q2 plus 1, and the product of all of these all the way up to the end. Okay. And that's definition of f of x. Like, just to like we can try to calculate 18. So our third number was 18. So you could say 6 3 is 18, which is 9 2 is 18. So 2 raised to power 1 into 3 raised to power 2. So you would have 1 plus 1 2, 2 plus 1 3, and 3 2 is 6. So 6 was our third number over here too. So that's how we would calculate f of x. Prefix of factorial, previous, fan of I, factorial. Okay, not really sure of factorial one, but yeah, fine. So now like how do we calculate the f of x? And the question is, so now we know how do we calculate f of x. Now how do we find this p1 raised to power q1, p2 raised to power q2, and all of these things? Now a of I is less than equal to 10 power 5. So you can just go from primes like from 2, 3, 5, 7, all the way up to something a of I, like at max a of I, the prime that's at max up to a of I, and then find it. Or there's a shorter way, which is that you can calculate the shortest prime factor for each of the x. Like the shortest prime factor would store, okay, what's the shortest prime factor of 2? It's 2. What's the shortest, smallest prime factor of 4? It's 2. What's the smallest prime factor of 5? It's 5. Okay, what's the smallest prime factor of 6? 6 is 2 into 3. So it has 2 as a prime factor, 3 as a prime factor. Then you would store 2 over here. So like basically you'd store the prime factor, smallest prime factor for each of this number. And this can be calculated with help of linear sieve. So that's one thing you could do, or you could do something like you could use other sieves to basically calculate all the primes, and sort of in I guess it's O of root n or something like that. But in this way, you can still factorize a of I into primes. So a of I is not really problem right now. So a of I is up to 10 power 5, and there are like good solid ways known to factorize numbers into primes up to 10 power 5. The problem is that you don't have to find f of a of I. You actually have to find f of a of I into m factorial. And m is less than or equal to 100, means that it can equal to 100. And 100 factorial is a very huge number. So 100 factorial is not something like we can calculate, or sort of like whatever, like we can't really calculate m factorial, then multiply it by a of I and then see how many factors it has. 100 factorial is going to be like a very huge number. It won't even fit in integers or long. So the question is, we can't really calculate 100 factorial. Can we factorize uh, m factorial, like not just 100, but any m factorial, without like calculating it? Like there some other way to factorize this thing, m factorial, without calculating it? Okay, yes, I guess a few of you know the answer. And before I tell you how do we do this, let's take an example. So let's just say 4, you have 1 2 3 and 4, like 4 factorials, 1 2 3 and 4, and that would correspond to like 2 ones are 2, 3 to the 6, and 6 fours are 24. What's 24? Well, 24 is 2 raised to power 3, that is into 3, like 8 threes are 24. Okay, so 24 has three twos, like 3 instances of 2 and 1 instance of 3. And what does this, so 24 has 3 instances of 2 and 1 instance of 3. Okay, 4 factorial is 1 2 3 and 4. How many 2's do you have? You have 3 2's according to this. How do you calculate this? Well, how many, like if some number has a 2 in it, then it would be divisible by 2. If x has a 2, then it would be divisible by 2, and it would contribute 1 2 to your 4 factorial. Okay, Then how many numbers divisible by 2 do you have over here? It's 2 and it's 4. So you have basically you have 4 divided by 2 numbers which are divisible by 2. Like basically between 1 to m, you have m divided by 2 numbers which are divisible by 2. In fact, for any k between 1 to m, you would always have m divided by k numbers exactly which are divisible by k. This kind of corresponds to one k, 2k, all the way up to m by k into k. You can go through prefixes. That's one way. Just a second. Okay. So, all right. And like what I'm trying to say is, so how many instances of 2 do you have? So any number that's divisible by 2 is going to contribute 1, 2. How many multiples of 2 do you have? You have 2 and 4. Okay, so you add 2 to your answer. Then are there any numbers which are going to contribute? So you have 1, 2, 3, and 4. So all multiples of 2 are going to contribute at least 1, 2 to your overall factorization. So 2 and 4 are going to contribute 1 and 1. Is there anything that's going to contribute more than 1, 2? So contributing 1, 2 means that x is divisible by 2. If x is going to contribute more than 1, 2, then it's going to be divisible by 4. If it's going to contribute more than 2 twos, like at least 3 twos, then it's going to be divisible by 8, and so on. Now, how many numbers divisible by 2 do you have? You have 2 numbers. How many, sorry, it's not x, it's supposed to be m. Up to m, how many numbers divisible by 2 you have? M divided by 2. How many numbers divisible by 4? M divided by 4. How many numbers divisible by 8? M divided by 3. Okay. All these are going to contribute at least 1, 2. All these are going to contribute at least 2 twos. All these are going to contribute at least 3 twos, and so on and so forth. Basically, if you add all these things, you get total number of twos that you can have, that you are going to have in m factorial. There's some problem. Power of primes, basically, yeah, right. So basically, the overall idea is that for prime p, there are m divided by p multiples of p in 1 to m. There are m divided by p squared multiples of p squared in this. These are going to contribute exactly 1 copy of p. These are going to contribute 2 copies of p, and so on and so forth, like m divided by p cube, and you could just go on up till like m is less than, greater than or equal to p raised to power k, and this would give you the power of p raised to power q. Then this is like in m factorial, if the power of p is q, then this would be like q would be like the sum of all these things. That's the like basic idea behind calculating the primes. And once you have these primes, like once you factorize m factorial, and you also factorize a of I for each I from 1 to n, like I'm using 1 based indexing over here, then what you can do is like for each of the i's, let's just say this factorization is factorization of, and this factorization of I. For each I, combine like this factorization of m and factorization of a of I, and then use that combined factorization to calculate your answer. Like basically, let's just go through an example to understand it better. So if we look at our example, okay, let's just take this example. In our example, we had m equal to 3. Okay, which are the primes up to 3? So primes are 2 and 3. So how many copies of 2 will we have? we have 3 divided by 2 plus 3 divided by 4 plus 3 divided by 8. Starting from here, all of them will be 0. So we actually only have one copy of 2. So 3 factorial is 2 raised to power 1 into how many copies of 3 do we have? We have 3 divided by 3 plus 3 divided by 9. This is going to be 0 and everything I add is going to be 0. So this will be 1. So we have exactly one copy of 3 factorial. Now, if we look at the factorization of 3, so let's just say that we have some data structure to store this. Here's the prime and here's the frequency of that prime. So for 2 and for 3, we have frequency of 1, 1. Okay. Now, what's our A of I? So A of I equal to 1 is simple. So let's just consider A of I equal to 2. What happens when you factorize 2? When you factorize 2, you get that 2 is itself a prime. There's only one prime. So you only get the prime is 2 and the frequency of this prime is 1. Now, to calculate the answer, that is to calculate f of A of I into m factorial, you need frequency of each prime and you need to basically multiply out frequency from of 1 plus all of these. And what you do is we basically try to combine to calculate the A of I into m factorial. We combine these two data structures. Like we'll store them probably in maps or something else. You can maybe try arrays, but if you let's just say store them in maps, like this is my prime and this is the frequency, this is my prime, this is the frequency, this is my prime, this is the frequency. Basically, you can combine both of these things to get the factorization of A of I into m factorial. That would be over here prime, this is the frequency. So your prime are 2 and 3. Here it was 1 and 1, so 1 and 1, and over here the frequency was like you add one more 1. Overall, you would get the frequency of 2 is 2, the frequency of 3 is 1. So this is your final factorization of A of I into m factorial. And like as we have discussed, like f of x is if x is like p1 into q1 something of this form, then this will end up becoming q1 plus 1, q2 plus 1, and so on. So basically, this would be frequency of prime 2 is 2. So your answer in this case would be like 2 plus 1 into 1 plus 1. This is 3, this is 2, so it would be 6. I guess that's the answer over here. So basically for this, we need to store all primes up to and pre-computing this, right? For this, I don't think you need to store primes up to 10 to the power 7. That's for the next problem. For over here, primes up to 10 power 5 would be fine. And then you basically have to calculate the factorization for m. M can be up to 100. So that would be calculated in at most 100 steps. And then what you can do is in this, what should I say? In this problem, what you can do is you can maintain the factorization for m factorial. And actually, this one thing, m is up to 100. So any prime that divides m factorial, so it has come from like 1, 2, 3, all the way up to m. So while m factorial can be large, the prime that can be in m factorial, they are very small. Like these primes that are present in the factorization of m, they are less than equal to m. And since m is less than equal to 100, there are at most 100 primes in m factorial. Like what I'm saying is you have 3 factorials, 1 into 2 into 3. 5 cannot be a part of 3 factorial because 5 is greater than 3 and none of these numbers can offer a 5 to 3 factorial. Basically, if you have m factorial and your prime is something say m plus 1 or m plus 2, it cannot be a part of m. And since the prime has to be less than m, so that implies that prime has to be less than m. So there can be at most m primes in factorization of m factorial. And get it. Okay, like let's look at the code and I hope it will be clear. So if there are any doubts, After that, we'll see them. So the first thing is, how many primes do you need? You need primes up to 10 power 5 because that's the limit on A. So you set max to this and mod it to 10 raised to power 9 plus 7. So I have used the normal sieve over here. This is not linear sieve. Basically what we're doing is iterate over all primes from 2 to max. If this thing is a prime, push this thing into the primes array, and for each of its multiples starting from 2 up to max, said mark this number as not prime because this is multiple of two numbers. And basically this is just calculating the number of primes, and I think this takes n log of n. And this part would pre-calculate all the primes. So pre-calculate all the primes and then call our solve function. Our solve function will take n and m. So we have to calculate m factorial into a of I for each of the a of I, a being an array of size n. And over here, we factorize m factorial. Okay, so what we do is we iterate over all the primes. Then if m is less than p, so say your m is 4, you're calculating 4 factorial, and your prime p is 5. Now, 5 is greater than 4, and 4 factorial is going to get all its prime from 1, 2, 3, and 4. So there's going to be no instance of 5 because the first 5 occurs at 5, and 5 is basically not included in 1, 2, 3, 4. So there's going to be no 5 in m factorial. And basically like this is, we maintain a power of p, and for each of this, like what's the frequency of p, like what's the power of p in the factorization of m factorial. And this is like kind of calculating this whole m divided by p plus m divided by p squared plus m divided by p cube, all the way up to this thing being not a zero. As long as this thing isn't a zero, this while loop would run, and this current would basically be like power of p. Initially it's p, then it gets updated to p squared, then p cube, then p raised to power 4, so on, unless and until like current is less than equal to m. When current exceeds m, then this would become zero and there's no point in continuing the loop. So this would give you a factorization of p. Then over here, like we are calculating b of I, and b of I is like get number of divisors. It's basically this function uh, f, and update frequency is basically we are merging, like calculating factorization of a of I and merging it with this frequency. And like finally we are outputting b of I over here. Let's just see what these functions do. So first, what update frequency does, it goes over all the primes, and we have this number x, so we are updating our frequency with this x. If this prime is greater than x, then you just break it. Otherwise, if x is divisible by this prime, then you update this frequency. Basically, like we have one more instance of this prime p, and we divide x by p, and we go on doing this as long as like x is divisible by p. So basically, as many instances of p you have in x, you just divide them out and increment your frequency those many times. And this is like kind of incrementing, like this is kind of, we take every instance of prime in this x and update our frequency array with that. So that's like update frequency. And then finally, this is get num divisors. Like we have a number that has prime factorization that's indicated by this frequency. Like we have prime 2 with this frequency, prime 3 with this frequency, and so on and so forth. What's the number of divisors that it's going to have? Modulo mod. Mod is defined above over here, 10 to the power 9 plus 7. How do we calculate this? So this prime has a power of f. So any divisor is going to have this prime with a power between 0 to f. Like the moment any divisor, like any number has a power of prime p f plus 1, then f primes are going to cancel out, and then you're going to be left with one prime below. So that won't be a divisor. So basically any divisor has a range of possibilities for this prime between 0 to f. Now 0 to f is basically f plus 1 possibilities. So you have one choice to make where you have f plus 1 possibilities. That basically indicates to your result being multiplied by f plus 1, and that would give you number of divisors. And yeah, like that's what we are doing overall over here. Basically, here we calculate the frequency of each of these primes, like frequency of primes in m factorial. Then this function updates this frequency with the primes in a of I, and this function takes this updated frequency, get number of divisors, and basically multiplies out the frequency plus one numbers and gives you the result. Yeah, sure, go ahead. And like any doubts up to this for how you're getting m factorial? Okay, so for m factorial, so if there's like this doubt for m factorial, so the question is, how do we get uh, prime factorization of m factorial? Okay, so let's take an example. Let's just say that m is 4. What's 4 factorial? 4 factorial is 1 into 2 into 3 into 4. Now, what's prime factorization? Prime factorization is basically you take a prime, let's just say prime p equal to 2, so 2 is a prime. And how many times does this prime occur in my 4 factorial? So 2 occurs, like here's 1, 2, and here's this 4, that is 2 into 2. So it has 2 instances of 2. So I have total 3 instances of 2. So here's my prime and here's my frequency. So we have 2 and we have 3 instances of 2. Now the question is, how do we come up, like derive that, okay, I have 3 instances of 2. Now notice one thing. So 2 can offer me how many 2's? Exactly 1, 2. Write this in. 2 can offer me 1, 2. 4, which is 2 cross 2. So it's offering me two 2's, like 2 instances of 2. If there was 8, it, and let's just not restrict ourselves over here. So 6 is 3 to the 6. So if there was any 6, then it is going to offer you one more 2. Then the next is 8. So 8 is 2 cross 2 cross 2. So it has 1, 2, 3 instances of 2. That's going to offer you 3 2's. Now, since you're going to multiply out all of these things in some n factorial, then you would have 1 plus 2 plus 1 plus 3. That's 7 2's if you add all of these. And basically now what you have to do is you have to somehow sum up all the instances that these things are giving. And now since the constraints on m over here are small, like one simple thing that you could do is you could iterate from I equal to 1 to m and just kind of factorize each of these i's and update your frequency. But for the harder problem, the formula over here is that how many instances of, like how many numbers offer me at least 1 2. So if you look at numbers offering you 2, you'll see that all of them are divisible by 2. So if you have some number x that is 2 into something, that means that x is divisible by 2. This means that 2 divides x. So that means that x is divisible by 2. Okay, so I have number from 1 to m. How many numbers are divisible by 2? How many numbers are divisible by 2? And this number is like something 1 to m. How many numbers are divisible by 2? Now, how many numbers are divisible by 2 in 1? 0. In 1, 2, there's exactly one number divisible by 2. In 1, 2, 3, there's one number divisible by 2. In 1, 2, 3, and 4, there are two numbers divisible by 2. Basically, you see, you take the last number, that's m, and divided by 2, and take the lower bound. That's the number of numbers that are divisible by 2. So all these numbers offer you 1 2, exactly 1 2, no, at least 1 2. So 2, 4, 6, 8, all of them offer you at least 1 2. All right, you take up this 2, like you have got now 4 2's, but you have a problem that these 4 2's aren't the only 2's. So if you look at 4, it's 2 into 2, so it has got two 2's, and 8, it has 2 into 2 into 2. So it has 3 2s. So it's basically offering you 3 2s. So you need to update your frequency array for these extra 2s. How do you do that? That now, since you know like which numbers offer you at least 1 2, you're dealt with numbers which offer you at least 1 2. The next point is which numbers offer at least 2 2s. Okay, which numbers offer you at least 2 2s? So look, like 4 offers you at least 2 2s, 8 offers you at least 2 2s, like it's 2 into 2 into 2. And any number, if that offers you at least 2 2s, it means it is somewhere 2 into 2 and then something else. And this means that this basically boils down to 4. So it means that this number is divisible by 4. All right. How many numbers between 1 to m are divisible by 4? There's exactly m divided by 4, lower bound. Numbers divisible by 4. If you want to work it out, 1, 2, 3, and 4, you have got one number. 5, 6, 7, 8, one number, all the way up to the end. And basically, you're kind of dividing it into blocks of 4, and at the end of each block, you're getting a number divisible by 4. So you have m divided by two numbers which have offer at least 1, 2. Then you have m divided by 4 number which offer two twos, like which offer up two, at least two twos. Now, for example, 4, it offers two twos. So it was counted once over here, and it is going to be counted once over here. And then you do something similar for three twos. Like how many numbers offer you up three twos? 8. Like 8 offers you 2 into 2 into 2. There are three twos in it. So it would be counted once because it's a multiple of 2. So it's divisible by 2. It would be counted once over here because it's a multiple of 4. So it's divisible by 4. And it would be counted once over here too because it's a multiple of 8, like 8 itself. So it's counted total 3 times. So if you look at it, basically what this does is, and this sum extended up to infinity, what this does is it gives you the total number of twos between 1 to m. Like that's the total number of twos in m factorial. That's the basic idea of what our factorial does. It's not intuition, it's more like a standard technique. So like the last three questions were, I guess, more or less dependent on a number theory. So it's a fairly standard formula in number theory. So if you study number theory, there like I don't remember the notation, but there it's like uh, the this is like the power of p in fact prime factorization of n factorial. Like this is the standard formula for that, and in there it's like extended up to infinity. But here, the moment you hit 0, we just stop calculating. So that's like something I am not exactly sure what's the notation for the power of p in n factorial, but it's some notation that's equal to this thing. So that's something fairly standard in number theory. And also one more thing, like in the previous problem, we had this f of x. You would usually see this as sigma or something of x. Like this basically denotes the number of divisors of x in number theory. And it also has some cool properties like sigma of a into b is a into b, given that your GCD of a and b is equal to 1. So it has some more properties, and there are a few theorems relating to it. So yeah, like something like did easy one we have prefixes, but hard one fail on prefixes. Learn new concept. Yeah, right. So I mean, more or less, the last three problems were heavily dependent on number theory. So if you had studied these things prior, would have been helpful. And right, so you could now that's overall how we calculate this frequency array. And I think in this problem it's m is up to 100. So basically, even if you brute force through I equal to 1 to m and calculate prime factors for each of them, that would work too. So I mean, that's how you calculate the frequency array for this. Then basically you take this A of I, update the frequency array, like take all the prime factors of A of I and increment the frequency array for them, and finally calculate the number of devices for this. So that was the core idea. And so that was the problem. I think it's problem D. And let's move to the next problem, problem E. Okay, no doubt. So let's move to the problem E. This was the hard version, the same like divisor arrays, hard version. And over here too, the overall problem was same. It's just that over here we had m is up to 10 power 7, a of I is up to 10 power 7. Now the core idea remains the same. First, factorize m factorial. Then, now previously what we did was we said update the factorization for a of I and like basically merge it with m factorial and then calculate, like the number of divisors. But in this problem, like when you try to the factorization for m factorial, previously m was up to 100. So you had at most 100 primes. In fact, less than that because there are very few primes. But in this case, m is up to 10 power 7. So your frequency array that can have not exactly 10 power 7, but let's just say in the hypothetical worst case scenario, you could have at max 10 power 7 primes where everything was a prime. That's not possible, but basically you would have a huge number of primes over here. So if you just go on and like in our previous problem, just go on and try to update frequency array for each a of I, that would lead to like something each time you'd have to iterate up to 10 power 6 7 elements, and you'd have to do that for all 10 power 5 n, and that would lead to TLE. So basically that would lead to something like big O of n into m time complexity, somewhere near this. And we don't want that. So because big O of n into m would be 10 power 5 into 10 power 7. So what we can do over here is, once you have calculated frequency array for m factorial, you can just basically calculate the answer for m factorial. What's the answer for m factorial? If m factorial is p1 raised to power q1, p2 raised to power q2, so on and so forth up to p2, pk into qk, we can just calculate the result for m factorial. This is like the number of divisors of m factorial. And now, when you're dealing with a of I, well, a of I is less than equal to 10 raised to power 5, all right? This implies that it has at most, I guess, around 10 to 12 prime factors. Reason is not 10 to 12, I guess. Let's just say at most 20, because I mean, 2 raised to power 10 is around 10 raised to power 3, and 2 raised to power 20 should be around 10 raised to power 6. So that would be like the overall. So you would have at most 20 prime factors. And now once you have this, let's just say you have prime 2 that has a frequency of 5, and you have previously calculated your result, and there your prime was 2 and your q was 3. So you are basically multiplying by 3 plus 1. And your actual result, where you are considering both a of I and m factorial, everything else, let's just say, remains the same. And for this prime of 2, your q, like the power, it is going to be 3 plus 5, 8. So it's actually going to be 8 plus 1. So what you want to do is you want to remove this 3 plus 1 and you want to multiply this 8 plus 1. That is basically like your result multiplied by, like, divide whatever frequency 2 already has, then add that frequency and the frequency of 2 in this new a of I and multiply it out. And you'd all at most have to do this for at most 20 primes. Actually, less than that, because I mean, with factorial, you would have at most 10, but let's just consider like 2 raised to power 20, so at most 20 primes. And so basically, like you just pre-calculate your res, and for each prime that you get in your factorization of a of I, you divide out the rest by its power and then multiply it out by the new power. A is less than or equal to 10 power 7. Okay, sorry. So a of I is up to 10 power 7, right? Uh, Even in this case, like, what's the worst case? In the worst case, you would have 2 into 3 into 5 into 7 into 11 into 13. So, like, actually look at it, like 2 into 3 into 5 into 7 into 11 into 13 less than or equal to 10 raised to power 7. And let's try to add a few more primes. It's 17, then 19. Okay, it takes quite a few primes. 23. So I mean, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have at most like 9 distinct primes. And like if you have more than 1 twos, then that would be 2 and frequency of 2. And you have at most 9 distinct primes, because like uh, so you have at most 9 distinct prime, and you have at most 9 updates to your res, and that would give you B of I. That's the overall idea. Like, calculate the res for m factorial, then uh, for each like prime and frequency of prime in a of I, what you do is you update your res to this new thing, where this res is first, what was the frequency of this prime in m factorial? It contributed this qp plus 1 to res, so remove that. Then what is going to be the new frequency of this prime? Well, whatever this frequency was in m factorial plus whatever this new a of I is going contributing to it, that's fp, and plus 1. Like, basically remove this, add this thing. That's what we are doing. And this involves like division modulo mod. So that was like one more caveat. Finally, uh, overall, if we look over here, I guess like this part was the most difficult one for most people, where you factorize m factorial, because I saw a lot of TLEs over there. And this is, you first calculate the result, like similar to last time. You take n and m, you take the array, input the array, factorize m factorial. Then over here, here's the different part. You calculate the number of divisors for m factorial, then set each b of I to this rest, that's number of divisors of m factorial. Then we factorize a of I. Get frequency is basically this function that factorizes x. And also over here, like, since the constraints are up to 10 power 7, what I've done is I've kind of used a linear sieve. So a linear sieve would basically give you what is the smallest prime factor for this number, and with that, like, it's more easier to get, like, you would get the factorization faster, I guess. And yeah, over here, like, we factorize a of I, then this prime is present with this frequency. Initially, this prime was present with this frequency in m factorial, so it contributed frequency of p plus 1. Divide that out from b of I. Now, b of I does not consider p when calculating its answer. So what's going to be the new frequency? It's going to the frequency of p that was in m factorial plus this f, the frequency in a of I. That's going to be the total frequency, and it's going to be, and it's going to contribute this plus 1 to your answer. So that's your answer, and this is your new updated b of I. All of this would proceed in, like, it is big of this divide function by my implementation would be log n. So something around this would run in O of m, and This would also run somewhere in the number of prime factors, like this would be big O of number of prime factors, worst case O of m, and this thing like somewhere near big O of n log n, like n log mod, and factorization itself takes n log n. So total sum, the time complexity would be something near your loop runs n times, and factorization itself, let's just say it takes big O of log n time. And finally, like those constant time operations dependent on mod and all those things. And the upper loop, it takes like big O of m time. This takes, while current is less than equal to actually big O of m into log of m, because we have that while loop that goes on iterating, and some other constant factors. So like overall, you could see that the time complexity big O of n log n into something plus big O of m log m into something. And with 10 power 7, you could kind of have a solution that would pass the constraints. All right, let's move to the final question. The final question was all equal. So we are given an array of length n and an integer k is said to be a good if the following condition holds. Basically, the greatest common divisor of a of I and k is same for all numbers. Like basically what this says is GCD of a of I and k is equal to GCD of a of j and k for all I less than j between 1 to n. This kind of meant that you needed the same GCD for all the numbers. And we defined f of a as the number of integers between 1 and m that are a good. So basically the number of k that are good with respect to a is f and f of a. And what we were given was we were given n and m, and we had to calculate sum of f of a over all m raised to power n arrays, because a of I could be between 1 to m. So basically what they are saying over here is you are given an array. So I'll represent a of I that is between 1 to m. Oh, sorry, this basically means that a of I is greater than equal to 1, less than equal to m, and this array has size of n, so there are n elements in it. And so basically for each element you have m choices, so this can have 1 to m for the first place, you can have 1 to m for the second place, so you have m into m into m all the way up to n times, so you have m raised to power n choices for the array. So there are m raised to power n arrays, and for each array you define this number as k good if like GCD of, so k is like good with respect to a if GCD of a of I and k is equal to GCD of a of j and k for all I less than j in the 1 to n. Basically, like what this is saying is, if you just expand this out, what we are saying is GCD of 1 and k is equal to GCD of a2 and k, which is equal to GCD of a3 and k, and so on up to GCD of a of n and k. Basically, every GCD of k with every number is same, and we have to find for each of these m raised to power n arrays. So f of a said how many good k do we have for a, and we have to calculate sum of f of a, where a is like part of this m raised to power n arrays, like m raised to power n arrays. I don't think this is the right notation, but yeah, like a is one of these m raised to power n arrays, and we have to calculate the sum of all of these f of a. And the constraints were n was up to 10 power 5, m was up to 10 power 5, and the number of test cases was up to 10 power 5, but the sum of n and sum of m over all test cases was less than equal to 5 times 10 raised to power 5. Sorry, m and n and m are up to 5 times 10 power 5. So that's the problem. And let's see the first test case. So I won't really I can't go the complete test case because like n, the answer is 10 power 5, so 25, so that would be a very large number. But overall, what we can do over here is we can construct an array where a of I is between 1 to m, and also this k has to be between 1 to m. So what we can do is we can construct an array where a of I is between 1 to m and the size of array is 1. So let's see, like, what can we do? We have 1, 2, 3, 4, and 5. And in this test case, I mean, it's very simple because you just have one element. So you can choose any k between 1 to 5, 1, 2, 3, 4, 5, and the GCD would be, this is 1, 2, 3, 4, 5, and GCD with 1 would be 1, 1, 1, 1. With 2, it would be 1, 2, 1, 2, 1. With 3, it would be 1, 1, 3, 1, 1. Like, I mean, since there's only a single element, there's no other element to compare to. So every k will be valid for every array. So there are 5 cross 5, it is 25 valid k, like 25 good k's. You have 5 good k's for this array, you have 5 good k's for this array, 5 good k's for this array, 5 good k's for this array, 5 good k's for this array. So overall, you have 5 plus 5 plus 5 times 25 good k's. That was problem 1. So let's take problem 2. So I think this will be more uh, in problem 2, you had a of I between 1 to 4, and the answer is 118. So you have a of I between 1 to 4. So let's just consider an array of this form. So you have 2, 2, 4, and 4. Okay. Now, according to definition, if you take k equal to 1, okay, what would be GCD with respect to 1? Okay, GCD of a and k. GCD of 1 and 2 is 1. GCD of 1 and 2 is 1. 1 and 4 is 1. 1 and 4 is 1. So the complete array is same. So k is good. Let's take k equal to 2. GCD of 2 and 2 is, this is k and this is a. So your a is 2, 2, 4, 4. If you take the GCD, you get this array. GCD of 2 and 2 is 2. GCD of 2 and 2 is 2. GCD of 4 and 2 is 2. 4 and 2 is 2. So the array is good. Like the k is good. And if we take k equal to 4 and our array is 2, 2, 4, 4, now you'll see that our k is not good. Reason, GCD of 4 and 2 is 2, GCD of 4 and 2 is 2, GCD of 4 and 4 is 4. So we have two different elements in our array. So k is not good. Not a good according to our definition, but yeah, k is overall not good because there are two different GCDs in here, and you can just assign this to I, assign this to j, and you will get a contradiction that GCD of a of I and k is not equal to GCD of a of j and k. That was the problem, and let's move to how do we approach this thing. Okay, first let's try to see what, so according to problem, like this k can be between 1, 2, 3, 4 all the way up to m, and for each array, like there are m raised to power n array. I think this is very bad, right? Looks better. So this is your array 1, this is your array 2, something like this, and you have m raised to power n such arrays, and your k could be between 1, 2, all the way up to m. And basically our problem said that for this array, look, is this k good? Yes. Is this k good? Yes. Is this k good? No. Okay. And you go on doing this all the way up to m. Let's just say m was good, and you count how many good k's do you have in total, and you tally that up as f of a, and you get some value, let's just say 4. Then you do the same for next array, say 5, 6 and something, and at the end you calculate the sum of all these f of a, and that's your answer. Okay. This would be like, this is according to our problem, but the problem is that there are m raised to power n arrays. We can talk about how we are going to iterate over k later, but there are m raised to power n arrays. So if we just go start iterating from over here and go down, 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 and basically try to iterate over all possible arrays, we have m raised to power n arrays to iterate over, and m and n are up to 10 power 5, 5 times 10 power 5. So 10 power 5 raised to power 10 power 5 is a large number. So we can't iterate over this. And we want to calculate this sum. So second, basically what we're doing over here. Now, if you look at it, what we're doing over here, we're calculating this green ticks, like basically k which are valid for this a. And so this is valid, this is valid, and this is valid. And we are basically summing up this whole row into this f of a, and finally just summing all of this f of a. This one more way in which we can do this. What we can do is say, I fix this k, and for this k, how many good a of I do I have? Like how many arrays there are where this k is good? Like basically how many green ticks, like how many uh, rows exist in this column where this k is good, and there are m raised to power n arrays. So we have to find some way to see how we can calculate this number. But if I can calculate this number in some efficient way, then we'll get a number over here, say 100. Then we'll get another number over here, say 10, and we can just sum up these numbers, and this too would equal to answer, basically, because answer is your basically number of ticks in this whole matrix. A tick indicates that this k is good for this array. And the good thing about this approach of iterating over columns, like basically counting the columns, is that there are only m columns. So our problem says that k has to be between 1 to m. Since k has to be between 1 to m, we can just iterate over all k's from 1 to m and find how many arrays there are for which this k is good. So what we can do is go from k equal to 1 to m, and we can maintain some result initially 0. Then we can just add for this k how many good arrays a, like such that k is a good. So how many arrays do we have such that k is a good in that array? Now this part is okay. We can iterate over this in big O of m time, and m is up to 10, 5 times 10 power 5. So this is okay. The question is, how do we calculate this thing? Now, are there any doubts? Okay. Now the point is, when is k a good? Like what do we mean when we say that k is a good? We are saying that the GCD of a1 and k is equal to the GCD of a2 and k, so on up to GCD of a of n and k. So all of these things are equal. Rather than trying to find array which can satisfy, like what I want to do right now is, I have m raised to power n arrays to deal with, and there's nothing common with these arrays, and m raised to power n is a very large number, so we can't deal with it directly. We have fixed k, so we know that we want to deal with k. Is there some other variable that we can fix so that we can have some constraint on these arrays and finally just get a count of how many arrays there are where k is good? So there's this condition, like if you look at the condition, k is good when GCD of k with respect to all a's is same. Let's just say that it's equal to d. All right. So what we are saying is GCD of a1 and k is equal to d. GCD of a2 and k is equal to d, and so on for all of these arrays. So k is good with respect to this array, and since it's good, all its GCD is equal, and let's just say that this GCD is D. Now what's a GCD? A GCD is divisor, like greatest common divisor. So a GCD is a divisor. So D is the GCD of A1 and K, A2 and K, and all of them. This means that D divides A1, D divides A2, all the way to D divides A of n, and D divides K. Okay. So we are iterating on K from 1 to M. We have found a way to fix K, and we know that other than K, we can also try to fix D. That's basically if K is good, then all GCD is going to equal, and there's this guy that's going to equal. And what we are trying to do is now kind of have some constraint on this m raised to power n arrays that we have, because we don't really know how to count which are the good arrays amongst them. So let's try to fix one more variable, that's D. So iterate for like K from 1 to M. Then can we iterate on all divisors of K? All divisors of K, that is D, such that D divides K. Basically, if your K is 4, then that would be 1, 2, and 4, something like that. Yes, we can do this thing. So this like this is something that we do when we sieve, do a normal sieve. The sieve of errors, something like when we do the normal sieve, what do? We go from I equal to 2 to some max value, and then we go from j equal to 2 to some max value. Basically, I into j less than equal to max value. Basically, what we are doing over here, we are iterating from I equal to, you can have from 1 to m, and then we can iterate from j equal to, even over here, j equal to 1 I into j less than equal to max. And basically, you're doing what we want over here, and we know that this has a time complexity of big of log of n for primes. I mean, in the worst case, you can just assume big of n log n, because there are we aren't marking any primes over here. So this is something we can do. So we can try to fix, we can fix K and D, and then see how many arrays there are such that GCD of A of I and K is equal to D for all I between 1 to n. So what we are trying to do right now, so just to summarize, we had m raised to power n arrays, and we couldn't go over all k's and calculate for them. So rather than iterating over m raised to power n arrays, we said that okay, we are going to iterate from 1 to m k, the value of k 1 to m, and see how many arrays, for how many arrays is this k good. Even then, like even when we fixed k, so we said that this is the k and how many good arrays there are. We don't really have any solid way of knowing, like out of these m raised to power n arrays, how many arrays are good with respect to this k. So then we tried to fix one more variable. We looked at our definition. Okay, we said that all GCDs are equal, and this guy D, let's just say it's equal to this guy D, then this D is actually dividing K. So maybe we can try to iterate over all divisors of K and fix, rather than just fixing K, we'll fix this pair K and D. So K is good with respect to an array of A such that the GCD of all elements with K is equal to D. So we have fixed these two things. Now, how many like arrays there are? And the most straightforward way, what you can do is, what's the range in which A of I is allowed to be? A of I is allowed to be between 1 to m. Okay. Then, is this equation dependent on anything else? Like if, say, you are constructing an array of size 4, so you have A1, A2, A3, and A4. Like the definition given in the problem was dependent that, okay, A of I has to be equal to, A of I has A of I, GCD of A of I k has to equal to GCD of A of jk. But now we have reduced it to this form where basically you just have to ensure that GCD of A of I and k is equal to GCD of d. What A of 1 is does not depend on what A of 2 is or A of 3 is. As long as A of 1 can ensure that GCD of A of 1 and k is equal to d, it's all good. Like 2 can be anything else as long as its GCD is equal to d. So what we can do is A of I can be between 1 to m. All right, so we can iterate from 1 to all the way up to m. If let's say we are iterating for x from 1 to m, if this GCD of x and k is equal to d, then we can set A of I to x. So we have one choice for A of I, and we can just kind of say that, okay, we have one choice for A of I, and we can basically see how many such x there are, and that's the number of choices we have for A of I, and we have n places to fill. And we can just say that, okay, we have these many choices for A of I, and we have n A of I. So it's basically like how many x do you have? Say you have fx such that GCD of x and k is equal to d, and you can just multiply them out n times. So like that's the overall idea, and now the question is how do we find this thing efficiently? Before going forward, let's just take this test case 3 and 4. So n equal to 3, m equal to 4, and say that you fixed k equal to 4 and d equal to 2. What we are saying over here is how many arrays there are such that every element has GCD of A of I and k equal to d, which is as good as saying that GCD of A of I and 2 is equal to d, not 2, sorry, k is 4, A of I and 4 is equal to 2. A of I can be in this range. Now m is 4, so A of I can be 1, 2, 3, and 4. Take the GCD with k, that is 4. What does the GCD end up being? It's 1, it's 2, it's 3, it's 4. Sorry, it's 1, 2, and GCD of 4 and 3 is 1, GCD of 4 and 4 is 4. So you only have this one choice. Let's just say that there were more choices. You had 5 and 6. GCD of 5 and 4 is 1, GCD of 4 and 6 is 2. So you have two numbers that are like that give a GCD of 2 when taken with k. So if your n was 4 and if this was your array, you had two choices over here. You could either place 2 or you could place 6, and that when you take GCD with 4, both of them would give you a GCD of 2. You could place 2 or 6 over here, you could place 2 or 6 over here, you could place 2 or 6 over here. Basically you had these two choices and n places to fill, so you would have 2 into 2 into 2 into 2, that is n times 4 times 2 raised to power n choices, like 2 raised to power n arrays, where GCD of A of I, k is equal to d. That's what this means. And now the question is, how do we find this 2? Like, how do we find the number of elements between 1 to m such that their GCD with k is equal to d? If we can find this thing efficiently, then we can take this number and just basically add up this number, say num raised to power n. We can just add up this thing, iterating over all k and d. So that's the idea up to this point. Like basically we iterate over all k, then we iterate over all the divisors of k, like d divides k. Then we find number of x such that GCD of x and k is equal to d, and this x is between the range 1 to m. And finally we add to our result, like basically for this k and for this d, each element has this number of choices, and there are n elements, so you could just have num raised to power n arrays, which when for which this k is going to be good, and every GCD is going to equal to d. And then finally, like we had to find what's this num. How do we find this num? Over here we'll use something called the inclusion exclusion principle. So this part is like slightly complicated to explain. Like basically what we'll do over here is, if like GCD of x and k is equal to d, that implies that d divides x. It's denoted by this, that d divides x. So x is a divisor of d. All right, x is a divisor of d. Sorry, x is a multiple of d, not a divisor, multiple of d. If x is a multiple of d, then how many multiples of d in 1 to m? Like how many multiples of d do we have in 1 to m? There are exactly m divided by d multiples. Like I think we discussed this in the previous problem. There are exactly m divided by d multiples. But there's a slight problem that, let's just say, I think let's say that let's take an example. Say our m is equal to uh, 2 into 3. Let's just say our m is equal to 6. 6, I mean. Let's just say we are watching for k equal to 6. We have m equal to 6. So we want to find all numbers between 1 to 6 that when taken GCD with 6 give you d equal to 2. All right. Now, if GCD of x and 6 is equal to 2, it implies that 2 divides x. So how many divisors of x do we have between 1 to 6? We have 1, 2, 3, 4, 5, and 6. This is a divisor of 2. This is a divisor of 2, and this is a divisor of 2. The problem is that all these are candidates for this thing, like GCD of x and 6 equal to 2. But you'll see that when taken GCD with 6, if you take GCD with 6, 2 will give 2, 4 will give 2, but 6 is going to give you GCD of 6. So this is not a valid x. So you only have 2x. Now, how do we get this 6? Like, how do we know that, okay, this I don't have to include, I don't want to include these things? That's where the principle of inclusion exclusion comes in. And basically, like what this thing says is, okay, how do we put this? Well, basically, like this allows us to calculate that I have this number k, and so we have this number k, and we have this d, and we have this numbers between 1 to m. So there are m divided by d divisors of m. Just a second, like I think we can simplify this a bit further. Like you have m divided by d divisors of m. So each of them is like d, 2d, 3d, all the way up to something. So it is x into d something. You can also represent k as k dash into d, because d is obviously going to be a divisor of k dash by those equations. Now, if you look at it, GCD of k and d is going to equal to d, because like d is a divisor of k, so that's always going to happen. And if GCD of x and d not x and d, x and k is equal to d, and say your x is equal to x dash into d and your k is equal to k dash into d, then GCD of x dash and k dash is bound to be 1. So like basically like what we are saying is we have fixed k and d and we are trying to find GCD of all such x in 1 to range of 1 to m such that GCD of x and k is d. What we are saying is if you just reduce k dash, this thing k dash, that is k divided by d, and if you reduce x to x dash, that is x divided by d, then both of these things are bound to have a greatest common divisor equal to 1. Why? Because let's just say 12, and so 12 is 4 threes are 12 and 9, so 9 is 3 threes are 9. This has a GCD of 3, so this is the common part. So this has GCD of 3 and the remaining part is not common, so this will only have a GCD of 1. If there was a GCD greater than 1, say even there was one more 3 over here, then you would have this 3 as GCD, so your total GCD would end up becoming 9, and that would be a contradiction. So basically once you remove out your GCD, the numbers that you are left with, they are co-prime, basically have a GCD of 1. And now if you look at it, like k dash is k divided by d, so and x dash is x divided by d. Now x is between 1 to m, so x dash is going to be between 1 to m divided by d, and that means our problem is find like number of co-primes of k dash, that is this thing, yeah, k dash in the range 1 to m divided by d. So any co-prime in this range would give us a x dash, and if you just multiply it out by d, then k and GCD of k and x dash into d is going to give you d. So you basically have one answer for your pair kd. And this problem can be solved in 10 raised to power 3 something, like basically like in this problem you want to find number of co-primes. Like your problem is now you have been given this k and you have to find number of co-primes of k in 1 to n, and we can solve this with inclusion exclusion principle. How do we do this? Basically what we do is first let's just say that all of them are co-primes, so consider k equal to 6, so k is 6, that is 2 into 3, and say that we have n equal to 8. Initially let's just say that all 8 are co-primes, like all 8 numbers 1 to 8, they give us a GCD of 1 when taken with k. Now iterate over all the divisors of k. So consider 2. How many multiples of 2 there are between 1 to 8? It's 2, 4, 6, and 8. Now what we do is all these are multiples of 2. So when you take a GCD with them, your GCD is going to be at least 2. So you subtract 4, like there are 4 multiples, so you subtract 4. Then look at 3. How many multiples of 3 there are? That is 3, 6, and 9 is not present. So these two are multiples of 3. When you take GCD of them with k, they are at least going to give you 3. So there are these two multiples, so you subtract them. Now 6 has been counted twice. So how do you deal with that? We'll take all the multiples of 6 and basically see, okay, how many multiples of 6 do we have? We have 1 multiple of 6, so it has been counted twice, so it was added once in here and it was subtracted twice, so you add it once, and basically like finally you got 8 minus 6 plus 1, that is 8 minus 5, that's 3, so that would correspond to 1, 2, 3, 4, 5, 6, and 7. So that would correspond to 1, 5, and 7 that are co-prime to 6 in 1 to 8. And the overall idea is that initially you go over all the divisors of this, you go over all the divisors of this K. Then if it has an even number of primes, then you say that res plus n divided by d. Otherwise, if it has an odd number of primes, then you say res minus n divided by d. So that's the overall idea. And this one more part, like if k is like 2 squared into 3, then you have to convert it into 2 into 3. That's to ensure that 2 is not double counted. Right, so this was the last problem, and let's look at the code for this problem. Taking input over here, test cases, and there are a few pre-calculations over here. We have this mod, like we have defined all this mod, and we have defined these mod functions. Then we have this max, and we are calculating pre-calculating all the primes, smallest prime factor. We iterate from 2 to max. Basically, this is a linear sieve where you pre-calculate the smallest prime factor for each I up to max. Then for each I up to max, from 2 to max, we calculate, does this number have an odd number of prime factor? Like this is basically, okay, you divide I by shortest prime factor of I that has one less prime and XOR it with 1. Also, like in this thing, like one thing I missed was that if you have something that has more than 2 primes, so if K has 2 cube into 3 or 2 squared into 3, you actually only need to consider 2 into 3, because the moment you consider all primes that have a GCD of at least 2, like all x with GCD with K at least 2, you don't really need to consider the ones with GCD of 4 or 8 and all those things. And if you have 2 raised to power 3 or 2 raised to power 2, that would complicate things a bit. So what we do is we just, if there's something like 2 raised to power 2 or 2 raised to power square, we just convert it to 2 raised to power 1 and then calculate all the numbers x that are co-prime with this, and that would by definition be co-prime with this too. So this is like we calculate the number of which numbers have an odd number of prime factors. And finally, we also calculate the divisors for each number. So we're just pre-calculating these things to save time later. Then, okay, so this function basically calculates the number of co-primes in 1 to n, the number of numbers in 1 to n that are co-prime with x. You start with res equal to 0, m equal to 1. This part is where we like basically eliminate if there are any 2 squared, then we convert it to 2. If there is any 3 cube, then we convert it to just single 3. And this is the part where we iterate over all the divisors of m, that is this reduced number with all only single primes. Then we see, does this divisor have an odd number of primes? If it has, then we subtract n minus d. If it has even number of primes, then we add n divided by d. And finally, we return our rest. This is basically the number of co-primes in the range 1 to n with respect to n. And this is the main function. We iterate over all d, k, d pairs, like k is the number that you want to make good, and d is the GCD of k and a and I. And finally, how many x, like how many choices do we have for a of I such that GCD of a of I and k is equal to d? Well, if GCD of a of I and k is equal to d, then if you divide a of I will be in range 1 to m divided by d. And if you take its GCD with k divided by d, then it's going to be equal to 1. So basically a of I is co-prime of k divided by d, and it's in range 1 to m by d. So what you do is you take the number of co-primes in 1 to m divided by d that are co-prime to k divided by d. That's your f. And finally, how many arrays there are where each number is one of these f, and there are n, the size of array is n. Like you have f choices for first, f choices for second, so on. So you have f raised to power n choices. That's your result. Like you add these many arrays to your result. So for each of these arrays, this k is a good k, and the GCD is d. And we can iterate over many more such, like for each k, we see how many arrays there are where this k will be good and will have GCD of d. So that's our overall iteration, and we just add these number of arrays to our answer and finally output our answer. Okay. So yeah, I mean, that was the final question, and yeah. So all right, that was the final question. Thank you for attending. All right. So since there aren't any doubts, I think we can end the PCD. Yeah. All right. Thank you for attending the PCD. Hope all your doubts were cleared. If there are any, do mention them. Uh, yeah.